Right now, everybody is building RAG systems. Upload some documents, create embeddings, store them in a vector database, retrieve chunks, and send them to an LLM. And suddenly, people think they've built intelligent AI systems. But there is a huge problem here. Most RAG pipelines are actually extremely fragile. They fail on complex questions, they retrieve irrelevant context, they hallucinate confidently, and the worst part, they have absolutely no idea when they are wrong. Traditional RAG works like a student taking an exam who is allowed to search through a textbook only once. One retrieval, one guess, one final answer. No reflection, no verification, and no retry mechanism, and no reasoning about whether the retrieved information is even useful or not. And that architecture is starting to become outdated because the next generation of AI systems doesn't just retrieve information, it thinks before retrieving. Modern AI systems can now rewrite their own queries, evaluate retrieved documents, detect poor context, retry failed searches, and dynamically decide what to do next. So instead of a static pipeline, we now have autonomous retrieval systems, and that is called agentic RAG. And in this video, we are going to build one from scratch using the LangChain ecosystem and LangGraph, a retrieval system that can reason, reflect, self-correct, and improve its own retrieval process autonomously. Not theory, not PowerPoint diagrams, and actual working implementation. Because simple RAG retrieves information, but agentic RAG learns how to retrieve intelligently. And honestly, that changes everything. So let's build it. Before we start building the system, we need to understand what actually changes when we move from traditional RAG to agentic RAG. Because at first glance, both look similar. You still have documents, you still have embeddings, you still retrieve context, and you still pass it to an LLM. But the real difference is not in the components, it's in the behavior of the system. Let's break it down. In a traditional RAG pipeline, the process is fixed. A user asks a question, we retrieve top K documents, and we immediately generate an answer. That's it. No decisions, no iteration, no intelligence in the pipeline itself. The system assumes one retrieval step is enough, and that assumption is where things start to fail. Because in real world queries, information is rarely perfectly retrievable in one shot. Some questions are ambiguous, some require better query formulation, some need multiple retrieval attempts, and some need completely different perspectives of the data. And this is where agentic RAG changes the game. Instead of treating retrieval as a single step, we turn it into a decision-making process. We introduce an agent that can control the retrieval pipeline. So now, before retrieving anything, the system can first rewrite the user query. It can ask itself, what is the best way to search for this? Then it retrieves documents, but it doesn't blindly trust them. It evaluates them. It checks, is this actually relevant to the question? And if the answer is no, it doesn't stop. It goes back, it refines the query, it tries again. It basically improves its own retrieval strategy. And this is the key idea. We are no longer building a pipeline. We are building a loop. A system that can reason about its own retrieval process. So instead of the flow query, retrieve, and answer, we now have query, plan, retrieve, evaluate, reflect, retry, and answer. And each of these steps is controlled by an agent. And this is why frameworks like LangGraph are powerful, because they allow us to build cycles, not just chains. So in the code you're about to see, we are going to implement exactly this loop. We'll build a query rewriter, a retriever, a relevance checker, and a reflection mechanism that decides whether to retry or proceed. And once you understand this pattern, you won't look at RAG the same way again. Because at this point, you're not building a chatbot, you are building a retrieval agent. Now let's go to the app part and start coding. So I have created this virtual environment in which I've installed the following libraries. You can create requirements.txt and install these libraries. So I also have this environment file here where I have kept my model API key. So I'm not going to show you this. You can use any model here. In this case, I'm using Groq library, and I'm using Llama 3.370 billion. So let's start coding now. And from LangGraph, import state graph and end. Now from LangChain Groq, let's import Groq. From LangChain core.documents, let's just do documents. I'm not going to ingest PDF file here. I'm just going to show you with some few documents that will be ingested into our agentic RAG here. So for that, I've used document from LangChain core. So again, from LangChain core dot prompts, we import chat prompt template. Now from LangChain community dot vector store, we are going to import Chroma. From LangChain community dot embeddings, we will import HuggingFace Embeddings. From LangChain text splitters, we are going to import recursive character text splitter. And then to load the environment file content, I'm going to do from .env import load.env. So first of all, I'm going to load the credential or the API key that I've placed inside my .env file. Now let me define my model. So the first thing I'm going to do is use Groq. I'm going to define my model name. Like I said, I'm going to use Llama 3.3 70 billion versatile model. You can go to the Groq documentation in LangChain and then see all the available models there. Now, as part of documents, now I'm going to create a few documents here. So since I don't want to type everything, so I'm just going to copy my list of documents from somewhere. So let me just paste this. So I have around 1, 2, 3, 4, 5, 6 documents. So remember, in place of these documents, you can just use your TXT files, PDF files, or any other kind of files that you need to ingest as in the form of knowledge base to your agentic RAG systems. Okay, so now that these documents are present, now my next step is going to be splitting these documents for as a part of chunking strategy. So first of all, I'm going to do splitter equals to, I already have recursive character text splitter library imported, so I'm going to use this. So here, first of all, I'm going to define my chunk size. So my chunk size is going to be 300, which means 300 characters. And then my chunk overlap is going to be 50. So right now, I think on no document that you see here will exceed the chunk size. So each of these documents will be placed as one chunk. But again, you can use your PDF file, ingest your PDF file as part of document, and then maybe separate out one single PDF into many different chunks, which will be better for retrieval later on too. So I've already done this in my previous videos. I hope you've seen those videos. So in this case, I'm just using a simple document case here. Okay, now let me use this splitter object that I've just created, and then use this splitter object to split documents that I have mentioned here, so which is raw docs. Okay, after this, let me define my embedding model. So my embedding model here is going to be HuggingFace Embeddings. So my model name will be all/mini LM L6 P. Again, this is from the HuggingFace library. You can use any other libraries that you want or any other models that you want. Just go to HuggingFace and then see the open source model there, or you can also use OpenAI or Gemini embedding models that are present. So the next step is a vector store or creating a vector store. Like I said, we're going to use Chroma as our vector store. So from documents, the source is going to be docs, which is this particular object here. Then as part of embedding, I'm going to define my embedding object that I just created earlier. And then since if I want to save my vector store for further uses too, so I'm going to use this persist directory key, and then let me just save it in a location, my vector store. Okay. Once this is done, we are going to go for retriever. So retriever equals to vector store dot as retriever. Let me define the how many results we want to achieve. So search keyword arguments equals to let me define this in this format. So we are retrieving not top 4, but we'll do top 3 result here. Okay, up until this point, this is a structured implementation of basic RAG, but since we're not doing basic RAG, we are going for agentic RAG. So now we will define our agent state here. So as part of our agent state, I'm going to define a class called agent state. This type will be type dict. So now I'm going to write down all the state components that our agent will have. So the first will be question, which will be in the form of string. If you want to write the description, you can even write that too there. Then we go for re-return question, because we are going to rephrase our question, or our agent is going to rephrase our question. So the re-return question. Then the retrieval part, which will be a list of documents, because we are searching for top 3 documents, so it will come as a list. Then our generation part, basically, which means the answer generating agent part. Then for the relevance checker agent, we will use a relevance library, and for the retry count, since we don't want our agent to go into infinite loop, so the retry count is going to be integer. So this is going to be my agent states here. So first of all, I am going to define my query rewriter agent. So for this, let me create a function, rewrite query state, agent state. And inside this, I'm going to write a prompt. So my prompt is going to come from chat prompt template dot from underscore template. Now inside this, let me write my prompt. So you are a query optimization agent. Rewrite the user question to improve retrieval from a knowledge base and make it more specific and semantically rich. So now my question will come as a question variable. I'll put it in a placeholder, and my prompt is well defined. So now I'm going to create a chain, which means first of all my prompt will be written, and then it will be called, or it will be sent to our LLM. So if I invoke this, so re-return equals to, I'm going to invoke this chain. So chain dot invoke I need to pass my question here. So question is going to be the state question, this particular state component here. And I don't want too much. I just want the exact answer that the LLM provides me. So let me print this re-return query. So let me just do /n and create a separator and then print re-return query. Let me just indicate this too. So re-return query. And what I'm going to do is I am also going to return this re-return query in the form of re-return question here. So return re-return question, and then in the value I'm going to provide the re-return query. Sorry, this should have been the re-return part. Okay, now our query rewriter agent is complete. Now let's go for retrieval agent. So let me define retrieval agent, def retrieve. So again, I'm going to pass in the agent state to this function here. So here I'm going to do query equal to state. Let me extract the re-return question that I've just passed in from here. Then after this, let me invoke my retriever. So retriever dot invoke query. Let me create a separator. Now let's print the retrieved docs. Retrieved docs. So, and after this, we're going to return this for documents to the state agent back. Okay, now my third agent is going to be a relevance grader. So for this, I'm again going to create a function called grade documents. Again, pass in the agent state here. So the question is going to come from state question. The retrieve docs is going to be received from documents. Let me create a context. So to create a context, I'm going to just join the documents. So for that, let me do dot join. For D in docs, let me extract D dot page underscore content. And finally, let me write a prompt for this agent too. So I'll be using chat prompt template dot from underscore template, just like earlier. Inside this, I'm going to define my prompt. Okay, so my prompt is going to be, you are a strict relevance evaluator. Determine if the retrieved context is sufficient to answer the question. Now here I'm going to pass in the question in the form of a placeholder question. Then I'm going to pass in context again in the form of a placeholder context. And let me add some more. So respond only with relevant or relevant. Okay, now like we did earlier, we'll write a chain. So first of all, I'm going to hit my prompt, and then after that I'm going to pass it to my LLM. So now I can invoke my chain. So chain dot invoke. I need to pass in two parameters. One is the question. So question is going to come from the question itself. And then the context is going to come from the context that I have created earlier here. I don't need everything. I just need the answer part. So dot content. I think that is okay for now. So let me check the result. Let me print it out. First of all, I'm going to print out a separator. Then let me print relevance result. So here I'm just going to print in the result, and I'm going to return this result back to the agent state in the relevance parameter. Okay, now the relevance grader part is also done. Now I finally need my answer generation part. So answer generation. So for that, I'm again going to create a function, pass in the agent state. Let me create a context using the document pages there. So slash n dot join, just like we did earlier. So for d in state documents, everything is going to come from documents there. I want to extract d dot page underscore content. Now for the prompt part, let me define a chat prompt template dot from underscore template and write down my prompt. So my prompt is going to be, you are an expert AI system designer. Answer the question using only the context below. So let me pass in the context in a placeholder again. After that, let me pass in the question again as a placeholder. Okay, now this part is also done. Add an indentation so that we won't get confused. These are all part of this function here. So now, just as above, let me create a chain LLM. Now I'm going to invoke this chain. So chain dot invoke. Like we did earlier, we need to pass in two parameters. One is the context. So context is going to come from the context object here, and the question is going to come from state question. Again, I only need the answer part, so let me just write down this, and then I can do return answer. No, it should be in generation. I think, let's see what the variable inside it. Okay, it is generation. So let me put this inside the generation part. Okay, all our agents have been now properly implemented. Now we need to write the logic for our final answer. So we'll create this logic here where the agent will identify if the answer is correct or not, or if it's need to be regenerated or not. So inside this, I'm going to check my relevance. So if relevance equals to relevant, then we can just go for generation, answer generation. So if the extracted documents okay, so what this means is if the extracted document is relevant, then we go for answer generation. We also have a a retry count here in our agent state. In order to enable or in order to prevent the model going from, or the agents going into infinite loop of irrelevance and then a regeneration. So let me check the retry count here too. So state retry underscore count. If this is greater than or equals to 2, I again want to go for generate. Else, if both of these conditions are not satisfied, or if the answer is irrelevant and the retry count is still within limit, then I want to go for rewrite. Okay, now for the retry tracker. So for the retry tracker, what I'm going to do is def retry tracker. I'm again going to pass in the agent state here, and that is going to be simple. So return retry count. So this is going to come from state retry count. Whatever the retry count is, I'm just going to go and do +1 here. Okay, so what did I do wrong? Oh, sorry, it should have been here. The indentation was incorrect, and then it should happen here. Okay, now everything is built. Now we need our agentic RAG workflows. So let me define my workflow here. And for that, I'm going to initiate a graph using a state graph object that we extracted from LangGraph. So state graph agent state. I think we imported it, right? Let's see. This should have been state graph. Okay. Now let me define my node. So graph dot add underscore node. This is going to be rewrite. First node is going to be rewrite. First function is rewrite query. Next node is going to be retrieve. First function is retrieve. Next node is going to be grade. This function is grade documents. Next node is going to be generate. Whose function is generate. And finally, we have for our retry logic. So the node is going to be retry. And then the respective function for this is retry tracker. Okay. Now, since everything is done, we need to set an entry point for this graph. Now we are going to build a workflow here. So graph dot set entry point. So where are we going to begin? We are going to begin with a rewrite. Basically rewriting the user query. Then from rewrite, I'm going to add edge, add an edge. So add edge. This will be from rewrite to retrieve. From retrieve, add edge. We're going to grade. Now, once we look at our grading agent, now we have a conditional route here, because after the grade, we need, or our agent needs to say whether this document is relevant or not. Now, if the grader agent says it's relevant, then we need to go to generate, or else we need to go to rewrite. Hence, we add a conditional edge here, because we have two different routes. So we add a conditional edge. So for conditional edge, we are going to start with grade. So from grade, then we implement this function here, which identifies whether the graded document has said to go ahead or regenerate or re-retrieve. So we either go to rewrite. If it is rewrite, then we go for retry. And if it is generate, then we go for generate. Now we'll add one more edge. So graph dot add edge. If we've gone to retry, we will go for a rewrite. And if we've gone to generate, then basically understand that the generated answer is the final answer, and we end the graph. Now finally we can do app equals to graph dot file. If we can print this, let me also print this graph. I'm not sure if we can do this or not, but let's see. Okay, now everything is done. We just need to provide the query here. So let me pass in a sample query. So my query is going to be .in. I'm just going to pass in the query directly inside my invoke function. So my question is going to be, why do production AI fail when dealing with multi-domain documents? Okay, so this is my question. And I'm also going to set my retry count to retry count 0. Okay, so whatever the workflow generates is going to be my final answer. So let me create a separator. And finally print result generation dot, okay, just generation part. Okay, so everything seems to be done. We started with importing our libraries. Then we moved to defining our model. Then we ingested some raw documents here, which could also be replaced by some files, PDF files, TXT files, and any other kind of files that we wanted our RAG system to handle. Then we went to a structured RAG workflow where we defined a splitter using a recursive character text splitter. Then we split our provided documents here. Then we converted them into embeddings using HuggingFace Embeddings and this particular model here. Then we stored the embeddings in our vector store along with creating a folder inside it. Then we defined a retriever where we basically asked for the top 3 queries. Then the normal or basic RAG would stop here, but we went on to defining the agent state since we wanted agentic RAG, and then we created some agents here. First of all, for the query rewriter. So for query rewriter, I basically provided this particular prompt here to rewrite the user question, and I also initiated the retry logic to 0 basically when I provided this particular query here. Okay, so the first part was the query rewriter. Once that particular query was rewritten by the agent, then we went for retrieval, where based on the rewritten query, the agent basically retrieved the relevant documents. Then we went for documents grader, where this particular agent graded whether the extracted document by the retriever based on the rewritten query was relevant or not. And then based on this, then we created this answer generation agent, which basically created the answer based on the extracted context or extracted documents and then the user provided question here. Now we created this particular logic to check whether our relevance grader had allowed us to generate the answer or asked us to rewrite the query for proper retrieval or not. Then we created a retry tracker function to basically count the number of retries that has happened inside this workflow. Then we went for the workflow. We added all of these agents into our node. Then we set the entry point as our query rewriter agent. From query rewriter, we went on to retrieve, and from retrieve, we went on to the grading agent. Now, from the grading agent, there were two pathways. So first of all, from grading agent, or if the grading agent said that the extracted documents were not relevant, then we basically went for the retry agent. Or if the grading agent said that the extracted documents were relevant, then we went on for the generate agent. Now, if we went to the retry agent, then that means the flow would have to be, or the flow would go to the query writer agent again. And if we went for the generate part, then it will basically mean the end of our workflow. And finally, I passed in the question here and then basically printed the answer at last. So now we can run this workflow and check what kind of answer we get, or basically how our workflow runs, or how our agents coordinate together to provide me a proper answer based on the provided documents. Okay, so I have opened my terminal here. Now basically I can do python app.py and then run this. Remember, you should install all of your libraries as provided here, and basically write the code correctly, and you can run it on your machine too. So let's see the output, what happens here. Okay, first of all, the models are being loaded. The HuggingFace embedding model weight are being loaded here. Okay, I think I made some mistake here. So found edge starting at unknown node retrieve. So where is this graph.compile? Let me check if we made any mistake here, basically in the workflow part. So there is let me also see the functions here. So this is retrieve, rewrite query, retrieve, grade documents, generate, and decide. Okay, so rewrite query, retrieve, grade documents, generate, and then retry. So when we went for rewrite, we went to rewrite, retrieve, and from retrieve to grade. This was correct. Okay, so what did we do wrong here? Let's see the prompt again. Found is starting at unknown node retrieve. Did we set start to retrieve? No, it went from rewrite to retrieve. Rewrite to retrieve and retrieve to grade. Let's see this if we made any spelling mistakes here. So retrieve is correct. This is retriever, this is retrieve, this is retrieve. Not sure what's wrong here. Let me check. Okay, so I think this was a simple spelling mistake here. So this should have been retrieve. And I think it's corrected. We'll run this and see if we have any more errors. Okay, I think we again made some mistake because even though it said relevant, but still went on to rewrite. Okay, let's check. What did we do wrong? First of all, let me go to this part. So if the relevance is relevant, okay, we did not check for the capital letter or the small letter part. Anyway, okay, so if we had just returned relevant here, then the query would have been stopped, or the agent would have stopped on the very first result. Anyway, we'll see how our agentic RAG went on. So my query was, why do production AI fail when dealing with multi-domain documents? So what did it do? It rewrote the query. To improve retrieval from a knowledge base, the question can be rewritten to be more specific and semantically rich as follows. So what are the primary challenges and limitations that current production artificial intelligence system faces when attempting to process and so on? So it rewrote the query. Then it went for the document retrieval. So it basically extracted 3 different documents here. 1 document, 2 document, and 3 document, because we had specified it to extract top 3 result. Then we went for our relevance checker. It had already said relevant, so it should have been stopped, but my logic here was wrong. I basically only compared the small caps relevant here, which did not match obviously, so it went for a rewrite again here. Okay, so what did it do in rewrite? Let's see. So in the rewritten query, it again rewrote the complete query, and it added much more detail to it. Then again it went to the document retrieval. Again, the grader said that it was relevant, but due to my error in logic there, we again took it to the rewriting query part. It again rewrote the query, the documents was retrieved, and then the grader said it was relevant. Now, since our retry counter has already exceeded our max threshold, so we directly went on to the generate part, and then the generate part produced me this answer, which is production AI system fails when dealing with multi-domain document because they often contain overlapping information across multiple domains such as finance and healthcare. So this was my final answer that I think was extracted from one of these documents. Let's see which document it did extract from. I think it was from this particular document here. So this is how agentic RAG works. So if it was a basic RAG setup, then we would have just provided it a question. It would have extracted the top 3 or top 4 documents, and then based on that, it would have generated an answer. But here we've included multiple agents to coordinate with each other and check whether the extracted documents are relevant or not, and then based on it, basically provide me the answer that I actually intend to. So this was the implementation for agentic RAG. I hope the concept as well as the implementation is clear to you. Sorry for the errors. I should have recorrected this as relevant, or basically I could also have converted this to a lowercase and then checked it in this particular way. But anyways, we saw how agentic RAG works here.
Over the last year, Retrieval-Augmented Generation or RAG has completely changed how modern AI systems work. But most RAG tutorials on the internet still follow the same simple principle. Upload a PDF, store embeddings, retrieve documents, send everything to an LLM, and generate an answer. And while that works for demos, that is not how production AI systems are actually built. Because once these systems enter the real world, everything starts breaking. Retrieval returns irrelevant context, hallucinations start appearing, latency increases, agents fail silently, and suddenly your working AI system now becomes impossible to trust. Modern enterprise AI systems are no longer just simple retrieval pipelines. They are becoming intelligent, modular, observable, and self-improving systems. Systems that can rewrite queries, evaluate retrieval quality, retry failed searches, re-rank documents, maintain memory, monitor performance, and dynamically orchestrate complex workflows. And this is where agentic RAG begins to evolve into production-ready AI architecture. And in this video, we are going beyond basic tutorials. We will break down how modern production-grade agentic RAG systems are actually designed, how different architectural layers work together, and what separates a toy AI demo from a scalable enterprise AI system. We'll cover ingestion pipelines, retrieval systems, agent orchestration, memory, evaluation, observability, modular architecture, and the core principle or the core engineering principle behind modern AI systems. So if you already understand the basics of RAG and want to level up into real AI systems engineering, then this video is for you. So before we start designing production-grade systems, we first need to understand why most RAG architecture fail in production. Simply because the majority of tutorials online optimize for one thing: getting a demo to work as quickly as possible. And that creates a very dangerous illusion. The illusion that RAG is simply retrieving some documents, attaching them to a prompt, and generating an answer. But real-world AI systems are far more complicated than that. Imagine building a customer support AI for a bank. Thousands of internal documents, policy changing constantly, multiple departments, large-scale concurrent users, strict compliance requirements, latency constraints, access controls, audit logging. Now suddenly, the simple vector database plus LLM architecture starts collapsing. Sometimes retrieval returns irrelevant chunks. Sometimes the most important documents never gets retrieved. Sometimes the LLM confidently hallucinates an answer. And sometimes the system fails silently without anyone even noticing. And the scary part is many AI systems look like they are working until users begin relying on them in critical environments. And this is why production AI engineering is fundamentally different from building AI demos. In production systems, we need reliability, we need observability, we need evaluation, we need scalability, we need modularity, and most importantly, we need systems that can continuously improve themselves. Because in reality, retrieval itself is an extremely difficult problem. A user query can be ambiguous. The retrieved chunks may lack context. The embeddings may fail semantically, or the user may not even ask the correct question in the first place. And this is exactly why modern RAG systems are becoming increasingly agentic. Instead of doing retrieval once and hoping everything works, modern systems can reason about the retrieval process itself. They can rewrite queries, evaluate retrieved documents, retry failed searches, use reflection loops, and dynamically identify how retrieval should happen. So the goal is no longer can we retrieve documents or not. The real question now becomes how do we build AI systems that can reliably retrieve the right information at scale? And that is where production-ready agentic RAG architecture begins. To answer that question, we need to shift our thinking completely away from linear pipelines and start thinking in terms of system architecture. Because in case of production, RAG is not a single workflow. It is a collection of interconnected systems working together. At a high level, a production-ready RAG system is typically broken into multiple layers. The first is the ingestion layer. This is where the raw data is collected, cleaned, chunked, enriched with metadata, and converted into embeddings. The second layer is the retrieval layer. This is where we search across vector databases, keyword indexes, or hybrid systems to fetch relevant context. But in real systems, retrieval alone is not enough. So we introduce a re-ranking layer. This layer refines the initial results and improve relevance using more powerful scoring models. Above that, we have the agent orchestration layer. This is where things start becoming dynamic instead of static. Instead of one fixed pipeline, we now have decision-making systems that can choose what to do next. Should we rewrite the query? Should we retrieve again? Should we use a different search strategy? Or should we proceed with generation? Then comes the evaluation layer. And this is what ensures the system is actually working correctly. Because in production, it is not enough for an AI system to sound right. It must be measurable, testable, and continuously evaluated. And finally, we have observability and monitoring. This is where we track latency, failures, hallucinations, retrieval quality, and system behavior over time. And when you connect all of these layers together, you no longer have a simple RAG pipeline. You now have a modular AI system, a system that can be improved independently at each stage, a system that can scale across use cases, and a system that can evolve as requirements change. And this is the fundamental difference between tutorial level RAG and production grade agentic RAG. In the next section, we'll break down the first critical component of this architecture, the ingestion pipeline, and why it plays a much bigger role than most people realize. So let's start with the ingestion pipeline, because this is where most RAG systems quietly succeed or fail before a single query is even asked. So in production systems, ingestion is not just about loading documents into a vector databases. It is a structured data engineering process. We begin with raw data sources. These can be PDFs, websites, internal knowledge bases, emails, support tickets, or even scanned documents. But raw data is almost never clean or ready for retrieval. So the first step is pre-processing. We remove noise, normalize formats, extract structured content, and handle inconsistencies across documents. Then comes chunking. And this is one of the most critical design decisions in the entire system. If you chunk too small, you lose context. And if you chunk too large, retrieval becomes noisy and inefficient. So, production systems often use smarter strategies like semantic chunking, hierarchical chunking, or parent-child chunking to preserve meaning while maintaining retrieval efficiency. And after chunking, we enrich the data. And this is where metadata becomes extremely important. We attach information like document source, section hierarchy, timestamps, access permissions, and domain tags. Because in real systems, context is not just text. It is structured information. Next comes the embedding generation. Here, each chunk is converted into a dense vector representation that captures semantic meaning. But even this step is not trivial in case of production. Different embedding models behave differently depending on domain, language, and document type. So, enterprises often evaluate multiple embedding strategies instead of relying on a single model. And finally, we store everything in a retrieval system. This could be a vector database, a hybrid search engine, or even a distributed search layer depending on skill requirements. At the end of this pipeline, we don't just have stored documents. We have a structured, searchable knowledge system designed for intelligent retrieval. And this is important to understand because if ingestion is weak, no amount of prompting, re-ranking, or agentic logic can fix the system later. In the next section, we will move into the retrieval layer, where we begin to actually fetch and reason over this information, and where most RAG systems start to show their first major limitations. So now that the data is properly ingested and structured, we move into the retrieval layer, where most RAG systems begin to feel either impressive or completely unreliable. At first glance, retrieval seems simple. You take a user query, convert it into an embedding, search the vector database, and return the top K results. But in production systems, this step is one of the most failure-prone parts of the entire architecture. Because semantic similarity is not the same as relevance. A query might retrieve documents that are topically similar but completely wrong in context. Or worse, it may miss the one critical document that actually contains the answer. And this is where traditional single-stage vector search starts to break down. So, production systems evolve the retrieval layer into a multi-stage process. The first stage is initial retrieval. Here, we often combine multiple strategies: dense vector search for semantic understanding and sparse keyword search for exact matches. This is also known as hybrid retrieval, and it significantly improves recall. But even after the hybrid search, we're still not done, because what we retrieve at this stage is only a rough candidate set. So we introduce a second stage, which is re-ranking. Instead of trusting the vector database ranking directly, we pass the retrieved documents through a more precise scoring model. This model evaluates relevance more carefully, often using cross-encoders or specialized ranking models. The goal here is simple: take a noisy candidate set and refine it into a highly relevant context. This two-stage approach, retrieval followed by re-ranking, is what makes production systems significantly more reliable than basic RAG demos. But even this is not enough in many cases, because user queries are often ambiguous, incomplete, or poorly phrased. And this is where we start introducing agentic behavior to retrieval itself. So instead of treating retrieval as a fixed step, we allow the system to reason about it. Should the query be rewritten? Should we retrieve again with a different formulation? Or should we expand or narrow the search scope? And this is where retrieval becomes dynamic rather than static. And once retrieval becomes dynamic, we are no longer building a simple pipeline. We are building an intelligent system that actively participates in the search process. In the next section, we will explore exactly how agentic workflows sit on top of this retrieval layer and how they turn a static system into a self-improving loop. Once retrieval becomes multi-stage and re-ranking is in place, the next major shift happens at the system level. Here, we introduce agentic workflows. And this is where RAG stops behaving like a pipeline and starts behaving like a decision-making system. In a traditional setup, the flow is fixed. User asks a question, system retrieves the documents, LLM generates an answer. But in production-grade agentic RAG systems, nothing is strictly linear anymore. Instead, we introduce control loops. The system can now evaluate its own retrieval result before generating a final response. If the retrieved context is weak, it can identify to retry. If the query is unclear, it can rewrite it, and if the search space is too narrow, it can expand it. And if the results are inconsistent, it can trigger a reflection step to improve reasoning before moving forward. This is the core idea behind agentic retrieval. Now, the system is no longer just executing steps, it is choosing steps. Frameworks like LangGraph make this possible by representing the system as a graph of nodes and transitions instead of a straight pipeline. Each node has a specific responsibility: query rewriting, retrieval, evaluation, re-ranking, or generation. And the edges between these nodes are conditional, meaning the system decides where to go next based on intermediate results. And this is what introduces loops into the architecture: retrieval loops, evaluation loops, retry loops. And this is where the performance improvements happen in real systems. Because instead of accepting the first retrieved result, the system actively improves its own input before answering. This dramatically increases accuracy, especially in enterprise environments where queries are complex and ambiguous. But more importantly, it introduces controllability. You are no longer hoping the model behaves correctly in one pass. You are designing a system that enforces correctness through structure. And once we introduce these agentic loops, we also need to introduce something really important: memory and state management. Because once a system starts looping and making choices, it must remember what it has already tried. So in the next section, we will explore how memory transforms agentic RAG systems from stateless pipelines into persistent intelligent systems. As soon as we introduce loops, retries, and decision making into the system, one problem becomes unavoidable: state management. Because an agent that cannot remember what it has already done is essentially blind. In a production-grade agentic RAG systems, memory is not just a feature, it is a structural requirement. We can think of memory in three different layers. The first is short-term memory. This includes the immediate context of the current interaction, the query, intermediate retrieval results, rewritten queries, and evaluation feedback. It allows the system to maintain continuity within a single reasoning cycle. The second is session or conversational memory. This is where the system remembers previous user interactions within the same session. It helps maintain context across multiple turns, so the system does not treat every query as isolated. And the third is long-term or semantic memory. This is where systems begin to behave more like intelligent assistants rather than stateless pipelines. They can store important information, learn preferences, or frequently access knowledge patterns for future use. But memory alone is not enough. We also need state tracking, because in agentic systems, every step matters. Did we already try rewriting the query? Did retrieval fail or succeed? Was re-ranking applied, or did the evaluation pass or fail? Without structured state, these systems quickly become unpredictable and hard to debug. And this is why features like or frameworks like LangGraph are so powerful. They allow us to explicitly define state objects that travel through each node in the workflow. Instead of losing information between steps, we carry it forward in a controlled and structured way. And this transforms the system from a black box into a traceable execution graph. And this traceability is critical in production environments, because when something goes wrong, we need to know exactly where and why it failed. Not just that the final answer was incorrect. Once memory and state are properly ingested or integrated, the system becomes significantly more stable and intelligent. But there is still one missing piece. We still do not know whether the system is actually performing well. And in production, it seems to work is never enough. We need measurement, we need evaluation, and we need observability, which is exactly what we will explore in the next section. So at this point, we have built a system that can ingest data, retrieve information, re-rank results, and even make choices through agentic loops with memory and state. But there is still a critical gap. We still do not know if the system is actually performing correctly. And in production environment, that is a serious problem. Because our RAG systems can appear to work perfectly in testing, but silently fail in real-world stage. It might retrieve slightly irrelevant context, it might generate partially incorrect answers, or it might drift in quality as data changes over time. This is why evaluation and observability are not optional components. They are core architectural layers. Evaluation answers a simple but powerful question: is the system producing correct and grounded outputs? In production-grade RAG systems, we evaluate multiple dimensions. We measure how relevant the retrieved context is. We measure how faithful the final answer is to that context. We measure whether the answer actually addresses the user query, and we often track hallucination rates as a key metrics. Frameworks like Raga's, DeepEval, or LangSmith evaluation allows us to automate this process so that every change in the system can be tested systematically. But evaluation alone is not enough. We also need observability, because evaluation tells us what is wrong. Observability tells us why it is wrong. And with proper observability, we can trace every step of the system execution. We can see the original query, we can inspect rewritten queries, we can inspect retrieved documents, we can inspect re-ranking scores, we can see which node in the agent graph made a decision, and we can measure latency and token usage at each stage. This level of visibility is what separates experimental AI systems from production AI systems. Without it, debugging becomes guesswork. With it, every failure becomes an engineering signal. And this is where tools like LangSmith, LangFuse, and Phoenix become extremely important. They allow us to turn black box LLM workflows into fully traceable execution systems. Once evaluation and observability are in place, we are no longer building experimental pipelines. We are building measurable, debuggable, production-grade AI systems. And now that we have all these layers in place, the final step is to bring everything together into a modular architecture that can scale, evolve, and be maintained by real engineering teams, which is exactly what we will cover next. Now that we've covered ingestion, retrieval, agentic workflows, memory, evaluation, and observability, the next question is how all of this actually comes together in a real system that can scale. Because in production, the biggest challenge is not building a single feature. It is maintaining a system that keeps evolving without breaking. And this is where modular architecture becomes essential. Instead of building one tightly coupled RAG system or RAG pipeline, production systems are built as independent modules that can be developed, tested, and upgraded separately. At the core, you typically have separate components for ingestion, retrieval, re-ranking, evaluation, memory, and orchestration. Each of these components should be isolated enough that improving one does not break the others. For example, you should be able to change your embedding model without rewriting your retrieval logic, or swap your re-ranking model without touching the ingestion pipeline. And this separation of concern is what makes large-scale AI systems maintainable. In real engineering teams, each module is often treated like a service. It has its own configuration, its own testing pipeline, and sometimes even its own deployment lifecycle. And this is how AI systems move from prototype to production-grade architecture. Another key aspect of modular design is orchestration. Instead of hard-coding logic in a single script, systems like LangGraph allow us to define workflows as explicit graphs. Each node represents a module, and the edges define how information flows between them. This makes the system not only modular but also visually understandable and debuggable. And when something fails, we don't need to guess where the problem is. We can trace it back to a specific module in the graph. And finally, modular architecture also enables scalability. Because when demand increases, you can independently scale retrieval sources or evaluation services without scaling the entire system. And this is how enterprise AI systems are built. Not as a monolithic pipeline, but as modular and independently evolving components. And once you understand this structure, you stop thinking about RAG as a technique, and you start seeing it as a full software system. In the final section of this video, we will connect everything together and understand what actually makes a RAG system production ready in the real world and how enterprise team thinks about deploying these systems at scale. So at this point, we have broken down every major component of a production-grade agentic RAG system, from ingestion to retrieval, from agentic orchestration to memory, and from evaluation to observability and modular design. Now, the final question is simple but important. What actually makes a RAG system production ready? Because it is not any single component. It is the way all these components work together under real-world constraints. In production environments, systems are not judged by whether they work. They are judged by whether they are reliable, scalable, and maintainable over time. A production-ready RAG system must handle real traffic, not just test queries. It must degrade gracefully when retrieval fails, not crash or hallucinate silently. It must be observable so engineers can understand every choices the system made. It must be evaluable so improvements can be measured objectively rather than assumed. And it must be modular so that individual components can evolve without breaking the entire system. And this is what separates experimental AI demos from enterprise AI pipelines. In a demo, correctness is enough, but in production, consistency is everything. And in real-world system, failure is not rare, it is expected. So, the system must be designed with failure in mind from the beginning. And this is why modern AI engineering looks less like prompt engineering and more like distributed system design. Because at scale, you are no longer just working with language models. You are working with pipelines, services, graphs, evaluation systems, and monitoring layers, all working together as one cohesive system. And when all of this comes together correctly, something powerful happens. RAG stops being just a retrieval technique. It becomes a full intelligent system architecture, a system that can learn, adapt, improve, and scale across real-world use cases. And this is the real shift happening in AI right now. Not just better prompts, but better systems. In the next video, we will take one of the most critical missing pieces of this architecture, re-ranking, and go deep into how it actually improves retrieval quality in real production systems. And that brings us to the end of this video. If you made it this far, you now understand something most AI tutorials never explain. How real production-grade agentic RAG systems are actually designed and structured in practice. We started from the limitations of basic RAG pipelines and then gradually built up the full architecture: ingestion, retrieval, re-ranking, agentic workflows, memory, evaluation, observability, and modular system design. And more importantly, you now have a system-level mindset for thinking about AI applications, not as prompts and responses, but as engineered systems. We explored how production-ready agentic RAG systems are built. We talked about ingestion pipelines, retrieval systems, agentic workflows, evaluation, observability, and the different architectural layers that makes modern AI systems reliable in production. But there was one component that we only briefly touched on, a component that often determines whether your AI system gives an excellent answer or a completely wrong one. And that component is re-ranking. Because here's the reality. Most RAG systems don't fail because the LLM is bad. They fail because the LLM receives bad context. Imagine asking a perfectly valid question. The answer exists in your knowledge base. The retriever even finds the correct document, but instead of ranking it first, it ranks it seventh. The LLM will never see it, and the final answer becomes incomplete, misleading, or entirely wrong. This is one of the biggest hidden problems in retrieval-augmented generation. And surprisingly, many developers don't even realize it's happening. They spend weeks optimizing prompts, changing models, and tweaking system instructions, when the real issue is that retrieval returned the wrong context in the first place. This is exactly why modern production RAG systems rarely rely on vector search alone. Instead, they introduce a second layer called re-ranking, a layer specifically designed to separate relevant documents from merely similar documents. And that is far more important than it sounds. In this video, we'll understand why vector search alone is not enough. We'll explore the limitations of dense retrieval, semantic similarity, and top-case search. We will then dive into how re-ranking works internally, how cross-encoders improve retrieval quality, and how popular solutions like Cohere re-rank, BGE re-ranker, and Gina AI re-ranker are used in modern AI systems. We'll also build a practical retrieval and re-ranking pipeline and see how re-ranking fits inside larger agentic RAG architectures. By the end of this video, you will understand one of the most impactful upgrades you can make to any RAG system, because often the difference between a mediocre AI system and a great one is not the model. It's actually the context. Before we understand how re-ranking solves the problem, we first need to understand why vector search often fails. And this might sound surprising at first. because vector search is incredibly powerful. In fact, it was one of the breakthroughs that made modern RAG systems possible. It allows us to search based on meaning rather than exact keywords. Instead of looking for exact word matches, vector databases search for semantically similar context. And that's exactly where the first problem begins. Because semantic similarity is not the same thing as relevance. Let me explain. Imagine a user asks, what are the loan eligibility requirements for self-employed customers? A vector database might retrieve documents related to loan applications, business financing, loan interest calculation, or self-employment verification. All of these documents are semantically related to the query, but only one of them actually contain the eligibility requirements the user is looking for. The retriever is doing exactly what it was designed to do. It is finding similar content, but similarity does not guarantee that the content is the most useful answer. This phenomenon is often called semantic drift. The retrieval gradually drifts towards documents that are topically related but not directly relevant. And as knowledge bases grow larger, this problem becomes increasingly common. Another challenge is embedding limitations. Embeddings are remarkable, but they're still compressed representations of language. They cannot perfectly capture every nuance, every relationship, and every domain-specific detail. A small difference in wording can sometimes lead to surprisingly different retrieval results. This becomes especially noticeable in specialized domains like banking, healthcare, legal systems, or technical documentation. Because domain-specific terminologies often carry meaning that generic embedding models struggle to fully understand. Then we encounter another issue, which is context fragmentation. Many answers are not stored neatly inside a single chunk. The information may be distributed across multiple sections of a document. One chunk contains the requirements, another contains exceptions, and a third contains important constraints. The retriever might only find part of the answer, creating incomplete context for the LLM. And finally, we have the famous top K problem. When performing retrieval, we typically ask for the top 5, top 10, or top 20 documents. But how do we know which value is correct? If we retrieve too much documents, we increase noise and we may distract the language model. While if we retrieve too few documents, we may miss important information. There is no universal number that works for every use case. And this creates a difficult trade-off between recall and precision. So when developers say my RAG system retrieved bad context, the issue is often not that retrieval failed completely. The issue is that retrieval produced a set of candidate documents that contains both good and bad results. And this is a key insight. The retriever's job is not necessarily to find a perfect answer. Its job is to find a pool of potentially relevant candidates. The real challenge is identifying which of those documents or candidates deserve to reach the LLM. And that is exactly where re-ranking enters the picture. Now that we understand the limitations of vector search, let's look at how modern production systems solve this problem. And the solution is surprisingly elegant. Instead of asking the retriever to find the perfect documents, we allow it to focus on something much easier, finding a broad set of potentially relevant candidates. Then, we introduce a second stage whose only responsibility is ranking those candidates more accurately. This gives what is known as two-stage retrieval pipeline. In a traditional RAG system, the workflow looks something like this. The user submits a query, the retriever searches the vector database, the retrieved documents are sent directly to the LLM, and whatever context happens to be retrieved becomes the foundation for the final answer. But in production system, there is usually an additional step in the middle. The workflow becomes query, retriever, candidate documents, re-ranker, best documents, and LLM. At first glance, this may seem like a small architectural change, but it has a massive impact on the retrieval quality. Because now each component has a specialized responsibility. The retriever focuses on recall. Its job is to find as many potentially relevant documents as possible. We don't expect it to perfectly rank everything, we simply want it to avoid missing important information. Then the re-ranker focuses on precision. Its job is to examine those candidate documents more carefully and identify which ones are the most relevant to the user's question. The separation of responsibilities is extremely important because retrieval and ranking are fundamentally different problems. One is about finding candidates, the other is about selecting winners. A useful way to think about it is this: the retriever casts a wide net, the re-ranker chooses the best fish. Without re-ranking, the LLM often receives a mixture of highly relevant information as well as noise. With re-ranking, the context becomes cleaner, more focused, and significantly more useful. And that directly translates into better answers, better retrieval quality, lower hallucination rates, and a more reliable RAG system overall. But this raises an obvious question. How does a re-ranker actually identify which documents are most relevant? What makes it smarter than the retriever? And to answer that, we need to look inside the mechanics of how re-ranking works. So, how does a re-ranker actually work? Why is it often able to make better relevance decisions than a vector database? To understand this, we need to compare how retrieval and re-ranking process information. When a retriever receives a query, it first converts the query into an embedding vector. Each document chunk in the database has already been converted into its own embedding vector. The retriever then compares these vectors using similarity metrics such as cosine similarity. The documents whose vectors are closest to the query vector are ranked higher. This process is incredibly fast, which is why vector databases can search through millions of documents in milliseconds. But there is a trade-off. The retriever never truly reads the query and document together. It only compares their compressed vector representation. And while this works remarkably well, it can miss subtle relationships that are important for relevance. This is where re-ranking takes a completely different approach. Instead of comparing vectors, the re-ranker directly examines the query and each candidate document together. So let's imagine the user asks, what are the loan eligibility requirements for freelancers? And after retrieval, we obtain 4 candidate documents. Document A talks about general loan policies. Document B contains freelancer eligibility criteria. Document C explains interest rate calculations. And document D identifies application procedures. The retriever might rank these documents based purely on semantic similarity. But the re-ranker takes each document and asks a more focused question. Given this specific query, how relevant is the specific document? It evaluates the query and document pair directly. As a result, it may assign scores to each of these documents. So notice what happened here. The re-ranker has effectively reshuffled the results. The document that actually answers the question rises to the top of the scoring, and the less useful documents now moves down. And this is why re-ranking is often one of the highest impact improvements you can make to a RAG system. It doesn't require changing your vector database. It doesn't require retraining your embeddings, and it doesn't require replacing your LLM. It simply improves the quality of the context before it reaches the model. Of course, the increased accuracy comes with a cost. Unlike retrieval, re-ranking is computationally expensive. The model must evaluate each query document pair individually, which means it cannot realistically score millions of documents. And that's exactly why we use it after retrieval rather than instead of retrieval. The retriever rapidly narrows the search space. The re-ranker then carefully analyzes the smaller candidate set. In other words, the retriever is fast while the re-ranker is smart. And together, they form one of the most effective retrieval architectures used in modern RAG systems. But what kind of models are actually used to perform this re-ranking? The answer leads us to one of the most important concepts in retrieval systems, which are cross-encoders. To understand cross-encoders, we need to briefly revisit how most embedding-based retrieval systems work. In a typical vector search setup, we use what is called a bi-encoder architecture. In a bi-encoder architecture, the query and the document are processed separately. The query is converted into an embedding, Each document chunk is also independently converted into its own embedding. Then we compare these embeddings using a similarity function. This separation is what makes retrieval extremely fast and scalable, because all document embeddings can be pre-computed and stored in advance. However, this same separation is also the source of its limitation, because the model never actually sees the query and the document together. It only compares their abstract representation. A cross-encoder works very differently. Instead of processing query and the document separately, it processes them together as a single combined input. For example, the model receives something like this: query plus document A, then query plus document B, then query plus document C, and so on. Each pair is evaluated jointly by the model. This allows the model to perform much deeper semantic reasoning. It can understand not just whether the document is similar to the query, but whether it actually answers the query. And this is why cross-encoders are significantly more accurate for relevance scoring. They are essentially performing a fine-grained comparison rather than a coarse similarity search. But this accuracy comes at a cost. Cross-encoders are computationally expensive because you cannot pre-compute document embeddings in advance. Every query document pair must be processed at a runtime, which makes them unsuitable for large-scale initial retrieval. And this is the key architectural insight. Bi-encoders are used for retrieval and cross-encoders are used for re-ranking. And together, they form a powerful two-stage system that balances speed and accuracy. And now that we understand the underlying model behind re-ranking, the next step is to look at how this is implemented in real-world systems. And more importantly, which tools and services are actually used in production to make this work at scale. Now that we understand the theory behind cross-encoders and why re-ranking works, the next question is very practical. How do we actually use this in real production system? Because in real production applications, very few teams train their own re-ranking models from scratch. Instead, they rely on optimized, pre-built re-ranking services and models that can be plugged directly into their retrieval pipeline. We'll take a look at the most commonly used options in production today. One of the most popular solutions is Cohere Re-Rank. It is a hosted API that takes a query and a list of documents and returns the same documents sorted by relevance. It is widely used because it is simple, fast, and highly accurate for general purpose use cases. Another strong option is the BGE Re-Ranker family. These are open source models that can be run locally or deployed in your own infrastructure. They are often preferred in environments where data privacy is critical or where companies want full control over their stack. Then we have Jina AI Re-Rankers. These are particularly strong for multilingual retrieval tasks and are becoming increasingly popular in global applications. All of these tools follow the same fundamental principle. They take a query and a candidate set of documents and they return a reordered list based on relevance. This makes them extremely easy to integrate into existing RAG applications. Now let's look at how a production pipeline actually changes when re-ranking is introduced. Instead of directly passing retrieved documents to the LLM, we insert a filtering and scoring stage in between. Then the flow becomes user query, retriever, which can be either vector or hybrid search, the top K candidate documents, the re-ranker, cross-encoder or API model, the top and refined document, and then the LLM for final response generation. In most production systems, K is intentionally kept high, often around 20 to 50 candidates. Then the re-ranker reduces this down to a much smaller and more precise set, often 3 to 10 documents. This dramatically improves the quality of context passed to the language model. And as a result, the final output becomes more accurate, grounded, and stable. Now that we understand the production tools and where re-ranking fits in the pipeline, the next step is to actually implement it. Now we'll move from theory into implementation and build a simple but production-style re-ranking pipeline. We will use LangChain for orchestration, ChromaDB for retrieval, and a chat Groq with Llama 3.3 70 billion model for final response generation. The idea here is not to build a toy demo, but to mirror how a real RAG pipelines are structured in production system. And first, we start with the retrieval layer. We load our vector database and perform an initial similarity search to get a larger set of candidate documents. This step is intentionally generous. We are not trying to get the perfect results here. We are only trying to get coverage. So we typically retrieve something like top 20 or top 30 documents, but in a practical case, that might not be appropriate. So we'll keep the top certain value as per our implementation. Next, we introduce the re-ranking layer. So in a production system, this is where we would typically call a cross-encoder model or a hosted re-ranking API like Cohere, BZ, or Gina. But for our implementation, we will simulate the same behavior by scoring query document pairs using an LLM-based relevance function. This allows us to clearly demonstrate the concept without introducing external dependencies. And once we have our candidate documents, we pass each document along with the query to a scoring function. Each pair is evaluated for relevance. Then we sort the documents based on their scores. And finally, we select the top and most relevant documents and pass them to the LLM. And this is where our LLM model comes in. It takes the refined context and generates the final grounded response. So now let's implement this step by step using LangChain.
Now let's look at the implementation part. We will start with a very basic setup where I have these following requirements in requirements.txt file. I also have this knowledge.pdf, which is going to act as my knowledge base. Now this particular PDF is a Python node that I prepared on my own. So this will be my knowledge base for my RAG. And then I also have this env file where I have stored my LLM API key as well as my HuggingFace API key, which I'm going to use for embedding. So now let's start with the import part. So first, let me import document loaders from LangChain community. So I'm going to load Py PDF loader. Similarly, from LangChain text splitters, let me import recursive character text splitter. Similarly, from LangChain community.vector stores, I think this is already deprecated. I think we can already or directly do LangChain underscore chroma now, but for now I think we can use this. Import chroma. Okay, and from LangChain underscore HuggingFace, I don't think this is installed. So let me quickly install pip install LangChain HuggingFace. And I'm also going to add the same in my requirement document. Let me copy this and then paste it in my requirements too. Go back to the code. Now once LangChain HuggingFace is installed, so I can use LangChain underscore HuggingFace, I'm going to use HuggingFace Embeddings. And from LangChain underscore Groq, I'm going to use chat Groq. This will be used to load our model. From LangChain underscore core dot prompts, let me import chat prompt template. Import chat prompt template. And from LangChain underscore core dot output parsers, let me import str output parser. And finally, let me import OS also from .env. We'll import load.env. So now that every import is complete, let's load the credential using this function here. And then we define an LLM, which is going to be our chat Groq model. So the model name, the model is going to be, or the model name is going to be Llama 3.3 70 billion versatile model. So I'm not going to run this on my own machine, but I'm going to use this as a cloud service for which I have the API key inside my environment file. Okay, anyways, let's also define the embedding model. So embeddings is going to come from HuggingFace Embeddings, And similarly, I'm going to give in the model name. So my model name is going to be sentence transformers all mini LM L6 V2. Okay. Now we've loaded our main LM as well as the embedding model. So now what we're going to do is we're going to define our PDF path. So for this project, the PDF path is inside data folder, and I have knowledge.pdf. Similarly, let me use a loader object from PyPDF loader to basically load my PDF from this PDF path. And after that, we'll use the loader object to actually load the text from our PDF. I can just print the number of pages here, but I think it's okay for now. Then we'll go for text splitting. We can do text splitter equals to, we'll use the recursive character text splitter class. Here I have to provide two different parameters. The first is the chunk size. Let's define the chunk size to be 500, and then we'll define a chunk overlap to be around 100 characters. Okay, we'll simply do a character text splitter here. Now we are interested in the number of chunks here, so created len chunks, which will give us the number of chunks. Also for that, I'll have to use the text splitter object dot, since this is my PDF document, so I'll need to use split documents and then provide document object that I get from here. So once I've splitted it into chunks, then I printed the number of chunks that have been created. Now what we need to do is let's create a vector store. So for that, I'm again going to give a path. Let's call it chroma path. Chroma path equals to where do I give it? Okay, let's do \chroma _ db. So we check if this path exists or not, or if the folder is present or not. Exist chroma path, and if this is not present, we're going to create a vector store. So vector store equals to, we'll use the chroma class dot from documents, and inside this we'll need to provide documents first, which is the chunks that will be stored. Then I'll pass in the embedding as the embeddings that I have generated, or the embedding model that I have defined here. And finally, I'll do this persist directory so that once it is created, the directory stays there, or the vector store stays there, and it does not load or create this vector store again for second, third, or fourth runs. Well, if this is already in the path, then I simply need to load my vector store. So for loading vector store, I can do vector store equals to chroma. Simply load this using persist directory. So this is going to be my chroma path. And the second parameter that I'll need here is the embedding function. The embedding function is going to be embeddings. Okay, now that we've done this, let's go down to the retriever part. So retriever equals to vector store dot as retriever. I'm going to mention how many parameters or how many documents we need it here. So it is going to be defined as the search keyword arguments, and I'm going to mention how many top key results will I need. So I'll put the value of k equals to let's do 10 for now, and then we will arrange it accordingly based on the number of chunks that is created. Okay, once this is also done, let us define our initial retrieval part. So we'll define a function for this. So def retrieve underscore docs. Let's pass in the query, and then the query is going to be in the form of strings. So we'll return retriever dot get relevant documents, and inside this I'm going to pass in my query. So based on the query, the retriever is going to basically find me the top 10 results from the created chunks. Now comes the main part which we're targeting in this video, which is the re-ranker. So for re-ranker, what we're going to do here is we are going to use our LLM as the re-ranker scoring function, and then based on its output, we are going to filter this top 10 results into maybe top 3 or top 5 results. So for that, we need to first write a re-rank prompt. So for writing a re-rank prompt, I'm going to use a chat prompt template dot from underscore template. Now inside this, I need to provide my prompt. So my prompt is going to be, you are a strict relevance evaluator. Given a query and a document, assign a relevance score from 0 to 1. Return only the score. So here I'm going to pass in the query as we discussed earlier in the theory part. We're going to pass a pair of query as well as the documents that we have, and then we're going to check the relevance of query and each document. So document is the actual document here. So this is going to be my prompt. Now let me define a re-rank chain. So the re-rank chain is going to first have a re-rank prompt. After that, we're going to pass it to LLM, and then after that, we're going to pass it to str output parser. Okay, so this is going to be my chain. Now, since I have to re-rank, or I have to get a re-rank score for all of these 10 documents one by one, so I will define a function where we'll do this in loop basically. So def re-rank documents, the parameters are going to be query and document itself. So let me create a list to save the created scores. So I'm going to run a loop here. So for doc in docs, which means every document from those top 10 result is going to enter inside this loop here. So I'm going to go to score text equals to re-rank underscore chain dot invoke. So after this, let me pass in few parameters. The first one is the query that I need to pass inside this particular prompt here. So my query is going to be the query itself, and then my documents, sorry, it has to be document just as per this placeholder here. So inside this, I'm going to go to doc.page underscore content. Okay, once this is also done, we will try to get a score, and because we've used str output parser, so we are going to get this in string here. So what I need to do is, let's try and we will try to convert this score that we get in string into float. So for that, let's do score underscore text dot strip. If we have any spaces, this dot strip will remove all of those spaces around it, or if it cannot generate a float value, for that I'm going to assign the score as 0.0. This is an exceptional case. And finally, what I'm going to do is I'm going to append this to score docs, and we get our first score. Then again, we look through the document. So out of 10 documents, the first document score is received. Then we again go to second document, we pass in the query, we pass in the second document page content, we generate a score, and then we again call, we again append that to the score docs, and then this loop continues until and unless we've completed with all of the top 10 documents that we have received. Okay, now once this is done, let's go out of the for loop, and then we will sort our score docs here. So let's sort this out. Okay, what do we sort this on? So we'll just write this equals to lambda x x1, and then we'll do reverse equals to true. Okay, so one mistake here. Let's replace this with equals to, so that this sorting part is also done. Then we will return scored docs. Okay, now that our re-ranking document part is done, now let's go for the answer generation. So for answer generation, let's write a final prompt. The final prompt again will be generated using the chat from template .from_template. Let me write down the prompt here. So you are a helpful AI assistant. Answer only from the AI assistant. Okay, answer only from the supplied context. If the answer is not present in the context, say I don't know. So I'll provide the context. This will be in, or this will go in the form of placeholder as context, and then I will provide a question. This will go in the form of question. So now let me invoke a final chain for answer generation. So this final chain will have final prompt, then we'll have an LLM, and after that we're going to have str output parser. Okay, now finally we can go on and then call this generate answer function. So we'll first define this generate answer function. So for this, what we are going to do is, so I have my query as well as I have my top documents also, right, sorted from here. So here inside this function, what I'm going to do is I'm going to aggregate all the context into one single string. So to do that, add 2 backslashes dot join, and then add doc page underscore content for doc in top docs, and then return final chain dot invoke. So in invoke part, I basically need to provide 2 parameters. One is the context. So for context, I'm going to provide the context that I've just created up there, and then the second part I have to pass in the question. So for question, I'll pass in the query. Okay, so once this is also done, now we will define the full RAG pipeline here. Again, remember, this is a basic RAG with a re-ranker only, and you can convert this into agentic RAG as we talked about in our earlier videos. So for this, let's define def RAG underscore pipeline. I'll pass in the query. Now query is going to come in the form of integer, and then I'll provide the top k value. By default, the top k value is going to be 5. Okay, so first step is the retriever. So to do that, I'm going to call retrieve docs equals to, I'm going to call the retrieve docs function and then pass in the query. Once this is done, the second step is the re-ranking part. So for re-ranking, I can just score docs equals to, I can call the re-rank documents function and then pass in the query, and it simply accepts the documents here. So I'm going to pass in the retrieve docs here. So what this will do is this will generate me a pair of document as well as scores. So now what I'm going to do is I'm going to define my top k results. So top k top documents will be a list top for top comma score in score docs, and then I only want the top k values here. I don't need anything more. Then the next step is the generation of answers. So for this, I can simply do answer equals to generate answer function. I'll pass in the query and then the top docs here. And finally, let me return answer as well as score underscore docs. So what this is going to help me with is if I even have a multi-part question, now it will not only based on a single context which only matches with the semantics of the query, but it also now checks the relevance using this scoring mechanism here. So even a multi-part questions can be answered here. So now let's test this with a single part question here. Let's go to the knowledge base, go to any topic in between here, and then we'll ask what these are. Okay, so I'm going to ask my RAG module about the primitive data types in Python, and then we'll see what kind of answer it provides. Go back to re-ranker. So the query is list me the primitive data types in Python. Once this is done, I can call my RAG pipelines. So answer rank docs equals to calling the RAG pipeline and pass in the query. Now let's print the final answer here, as well as let's also print the top documents. The top docs. Sorry. Let's also print the ranked docs here. And basically, I'll only need 5 ranked docs. Let me convert this to string so that everything becomes easier to observe. So this will be my string. Let's add a line break /n so that we don't get confused what's happening. Okay, so we are ready to run this. So let's run python re-ranker rag.py. If we have any error, then we'll debug this. We should not have any error, but let's see. So we ran into an error where it says PyPDF is not installed. So we'll install PyPDF directly using pip. This library is required for the PyPDF loader that we have used there. So let me install this, clear this out, and then run it again. It's not PyPDF. Let me run the re-ranker. Okay, we still have some spelling mistakes here. So I think it should have been chunk overlap, but I think I made a mistake. So this should have been chunk overlap. Let me clear this out again and then run my RAG re-ranker again. Okay, so as you can see, 72 chunks were created, which means at first we are only trying to retrieve the 10 chunks. We still have some errors. So let's see, cannot access local variable retrieve docs. So where is this error exactly? In RAG pipeline and then retrieve docs, line number 110. So let's check this out. Line number 110. So retrieve docs is not a function. Let's see. Yes, it is a function. So retrieve docs is a function. We'll keep this name something else. So retrieve document, we'll keep this as retrieve document and then keep this as retrieve docs. Let me check the indentation again if there is anything wrong here. No, there's nothing wrong here, so I can just go ahead and then run this. Get relevant chunk. I think one more mistake that I saw here is I put an underscore just before this, so this should have been get relevant documents. Get relevant documents. Okay, I think the previous one was correct. Save this and then run it again. So the vector store is already created, so that process is not going to repeat because we have kept it in if and else part. Get relevant documents, missing one required keyword on the argument, which is run manager. Okay, so let me check what the error is. Okay, the first mistake that I see here is I think this won't work, so we'll need to use invoke. So after this, in the re-rank part where we have tried to append just the docs here, so what I want to do here is not only append doc but score here, but I also want to append the document part along with the score, so that x1 can finally be a score, and then the sorting can happen because of this score. Now again, let's clear this out and then try to run this again. If we run into any more errors, then I'll try to debug it. Okay, so we have our answer. So first of all, we're going to check the answer. So at first, what our model says is that the primitive data types in Python are integer, floating point number, string, and boolean. Let's go to the document, and I think we just have integer, floating, float, and string, and then boolean. Now let's go and check the re-ranking part. So for the re-ranking part, I see 5 basic data types. Python supports something. Okay, this is also generated, and along with that I see some more pages here which says Variables and assignments, page content 4, page content 5. So then we have some more document that contains the examples too. So I think it is working quite well. Now we'll try to ask a multi-part question. One is the data type that we'll ask, and then let's go down to something else or to some other topic, and then we'll ask what are frozen sets here. So let me update my query and then ask, list me the primitive data types in Python and tell me about what frozen sets are in Python. So this is kind of a multi-part question. So we'll try to check if my re-ranker does actually work in finding me the context for this two-part question and then answer me accordingly. Okay, so what this does is it does provide me about the data type, but it says that it does not know about frozen sets in the given context. So let me check. Okay, we do have frozen sets in the context, and then we have it inside sets. So I think the one problem it faced that it could not separate out the frozen set context, as well as it could not bring that in the document list inside here. I think that is the problem. Okay, we'll try with something else. Let's go ahead to the very top and then ask something. Okay, we will ask about the key branches of Python programming. So we'll keep the primitive data. Okay, we'll remove the primitive data type too. So first of all, we'll ask about the key branches of Python programming, and then we will ask which IDs can be used for Python programming. So let me change this question. So tell me about key branches of Python programming and list me which IDEs can be used for Python coding. Save this, clear the terminal, run it again, and then check. Okay, so let's see what the answer is. So it says the context does not provide about, wait. So it does give me the key branches of Python programming as web development, data science, and scientific computing. However, the context does not provide information about the IDs that can be used for Python coding. I don't know about the list of IDs for Python coding, and it is not present in the context. So since we're not getting the second part answer, so what we can do is we can try to elaborate the number of retrieved documents. Let's go down to 20 documents, the top 20 documents for this, and then what can we do more? Let's see. Then in place of the top key results, let's narrow down this to maybe 10 documents and then check. If even this does not give us an result, what we can do is we can have a query rewriter agent, which we can basically assign the task for breaking such two-part questions into multiple questions, and then we can search the query according to that, and then generate an answer in a combined form. But we'll check what happens here, and then we can try that, or you can try that later on if you want. Basically, since we are working with agentic RAG, so you can have a query rewriter part which you can prompt in such a way that if it sees a two-part question, you basically ask it to divide into two parts and then push it for working. So let's see if the context did find out. Okay, so it did find out the context. So improving the number of top key results did help. So here the key branches of Python programming language, well, now it is much more detailed. And then for Python coding, the following IDEs can be used with Jupyter Studio as well as Visual Studio Code. So these are the only IDEs mentioned in the provided context. Well, they are mentioned in the provided context here. We have Jupyter Notebook as well as the VS Code, but it could not identify PyCharm as an ID, but that's fine because it has reached up to this point and then found the context. So this is what re-ranker is, and this is how we implement re-ranker in our RAG in Python. But remember that this is implemented in a basic RAG, and then you can still implement it in your agentic RAG using the same approach that we did in our last few videos, plus this re-ranking part.
So far, we have built a clean re-ranking pipeline using vector retrieval followed by scoring layer that improves relevance. But in real production systems, retrieval is often even more complex than this, because vector search alone is not only a retrieval method used in enterprise AI systems. In fact, many high-performance systems combine multiple retrieval strategies before even applying re-ranking. And this is where hybrid search comes in. Hybrid search combines two different retrieval approaches. The first is dense retrieval, which is based on embedding and semantic similarity. And then the second is sparse retrieval, typically using keyword-based search methods like BM25. Each of these approaches have their own strengths and weaknesses. Dense retrieval is excellent at understanding meaning and context, but it sometimes struggles with the exact keyword matches. Sparse retrieval is extremely good at exact matches and rare terms, but it fails to capture semantic meaning. So instead of choosing one over the other, production systems combine both. This produces a richer and more diverse set of candidate documents. Now the pipeline becomes more powerful. We first perform hybrid retrieval, which gives us a strong pool of candidates from both semantic and keyword-based search. Then we pass this expanded candidate set into the re-ranking layer. The re-ranker then performs its job as before. It evaluates each document in relation to the query and selects only the most relevant ones. So the final architecture now becomes query, the hybrid search, which includes BM25 plus vector search, the candidate documents, re-ranker, the top key relevant context, and then the LLM. Now this combination is extremely powerful in production systems because hybrid search ensures we do not miss critical documents due to embedding limitations. And re-ranking ensures we remove noise and refine relevance before generation. And together, they solve both sides of the retrieval problem, recall and precision. At scale, this is the architecture used in many enterprise-grade search systems, especially in domains like legal AI, banking systems, and customer support automation. Now that we understand how hybrid retrieval improves candidate generation, the next important question is where exactly re-ranking fits inside a full agentic RAG system. Because re-ranking is not a standalone trick. It is one node inside a much larger decision-making system. Now let's place re-ranking inside the bigger picture, the agentic RAG system we discussed in the previous video. Because in production systems, re-ranking is not an isolated improvement. It is a decision-making point inside a larger reasoning loop. So let's reconstruct the full flow. A user submits a query, but instead of directly retrieving and answering them, the system first enters an agentic workflow. The query may be analyzed and rewritten if needed. Then retrieval is performed using either vector search or hybrid search. At this point, we do not immediately pass the results to the LLM. Instead, the system triggers the re-ranking layer. And this is where candidate documents are evaluated and refined. Only the most relevant context is passed forward. But in agentic systems, even this is not the final step, because we now introduce evaluation. The system checks whether the retrieved context is actually good enough to generate a reliable answer or not. If the context quality is low, the agent can choose to retry retrieval. It may rewrite the query again, it may adjust the search strategy, or it may expand the retrieval scope. Now, this creates a loop: retrieve, re-rank, evaluate, retry, improve, and generate. And this is where re-ranking becomes extremely powerful, because it reduces the need for repeated retries by improving context quality earlier in the pipeline. In other words, better re-ranking means fewer failed agent loops. And that directly improves the system efficiency, latency, and cost. So in a full agentic RAG system, re-ranking sits right between retrieval and evaluation. It acts as a filter that stabilizes the entire reasoning process. Without it, agent systems often become noisy and inconsistent. With it, the system becomes far more production ready. Now that we understand where re-ranking fits in the architecture, the next question is just as important. When should you actually use re-ranking, and when is it unnecessary overhead? So the next question is practical. When should you actually use re-ranking in a real system? Because while re-ranking is powerful, it is not always required. In fact, blindly adding it to every RAG pipeline can sometimes introduce unnecessary latency and cost. So let's break it down in a production mindset. Re-ranking becomes extremely valuable when you're working with large and noisy knowledge bases. For example, enterprise document systems, customer support databases, legal repositories, or internal banking knowledge systems. In these cases, retrieval alone often produces many partially relevant or misleading documents, and the cost of showing the wrong context to the LLM is high. So, the improvement in accuracy from re-ranking is worth the extra computation. Re-ranking is also very useful when queries are complex or ambiguous. If the user question does not map cleanly to a single document, retrieval tends to scatter results across multiple topics. Re-ranking helps bring focus back by selecting the most relevant interpretation of the query. It is also critical in high-stakes systems. Anywhere correctness matters more than speed, such as healthcare, finance, compliance systems, or enterprise decision support tools, re-ranking becomes almost mandatory. However, there are cases where re-ranking may not be required. If you are working with small datasets or highly curated knowledge bases where retrieval is already precise, adding a re-ranking layer may not provide significant improvement. Similarly, in low latency applications where response time is more important than slight accuracy gains, you might choose to skip it. The key takeaway is that re-ranking is not a default requirement. It is an optimization layer. So one that you introduce when retrieval quality becomes a bottleneck. And in most real-world production systems at scale, that bottleneck eventually appears. So while it may not be needed at the beginning, it often becomes essential as the system grows. Now that we understand where and when to use re-ranking, let's wrap this video and connect everything that we have learned into a final summary. So let's bring everything together. In this video, we started with a simple but critical problem in RAG systems. Why do AI systems sometimes give wrong or incomplete answers even when the information exists in the knowledge base? And we traced that problem back into its root cause, which is retrieval quality. We saw that vector search, while powerful, is fundamentally limited by semantic similarity. It retrieves documents that are related but not always the most relevant. This leads to issues like semantic drift, noisy top-tier results, context fragmentation, and embedding limitations. And to solve this, we introduced a second stage in the retrieval pipeline, which is re-ranking, a mechanism that evaluates every query document pairs directly and reorders results based on true relevance. We explored how cross-encoders make this possible by processing the query and document together instead of independently like by encoders. We also looked at real-world tools like Cohere re-rank, BGE re-rank, and Gina AI re-ranker that make this process scalable in production systems. Then we implemented a practical pipeline using LangChain and Groq, where retrieval results are refined before being passed to the LLM. And after that, we extended the idea further into hybrid search systems, combining dense and sparse retrieval to improve candidate coverage. And finally, we placed re-ranker inside a larger agentic RAG architecture where it works alongside query rewriting, evaluation, and retry loops to improve overall system reliability. The key idea you should take away from this video is simple. Vector search retrieves candidates, re-ranking selects the best context, and in real production systems, the quality of your final answer depends far more on the quality of your context than on the model itself. Because even the most powerful LLM cannot produce a good answer from bad or incomplete information. In the next video, we will go even deeper into production AI system and explore more advanced concepts that make these architectures scalable and enterprise ready. In the previous video, we built something most RAG tutorials never go beyond. We designed a production-ready agentic RAG architecture. We improved retrieval using re-ranking, and we saw how modern AI systems are not just pipelines, but layered decision-making systems. But there is a critical question we still haven't answered. How do we actually know if any of this is working correctly? Because in real-world AI systems, looking correct is not the same as being correct. A RAG system can produce fluent, confident, and well-structured answers and still be completely wrong. It can retrieve documents that look relevant but still miss the actual answer. It can pass basic evaluation but fail silently in production when real users start interacting with it. And this is where most AI systems fail in practice. Not because they're poorly built, but because they are never properly measured. In production environments, if you cannot measure your system, you cannot improve it. And if you cannot improve it, you cannot trust it. And this is why evaluation is not an optional step in RAG systems. It is a core engineering requirement. In this video, we are going to break down how real RAG systems are evaluated in production. Not just does it work, but how well does it work, why it fails, and where it breaks. We will explore how to measure retrieval quality, how to evaluate generated answers, how to identify hallucinations, and how modern frameworks like Ragas, DeepEval, and LangSmith help automate this entire process. Because once you understand evaluation properly, you stop guessing whether your system is good, and you start knowing it with data. So, we'll begin by understanding why evaluating RAG systems is much harder than it looks. At first glance, evaluating a RAG system seems straightforward. Ask a question, look at the answer, identify whether it is correct. Simple, right? Unfortunately, real-world RAG systems are far more complicated than that. Because unlike traditional software, AI systems are not fixed. If you run the same piece of software twice with the same input, you expect the same output. But with language models, output can vary. Different wordings, different reasoning paths, different answer structures, and sometimes multiple answers can all be considered correct. This immediately makes evaluation more challenging. But the complexity doesn't stop there. A RAG system is not a single component. It is actually a collection of multiple components working together. First, the retrieval system must find the right information. Then, the re-ranking system must prioritize the best context. Then, the language model must generate a grounded response. If the final answer is wrong, where exactly did the failure occur? Was the answer missing because retrieval failed? Did re-ranking push the correct document too far down? Or did the language model hallucinate despite receiving the correct context? Without proper evaluation, it becomes almost impossible to know. And this is one of the biggest challenges in AI engineering. A single bad answer can have multiple root causes. Another complication is that there is often no single ground truth answer. Consider a question like, what are the benefits of hybrid retrieval? One person might provide a concise explanation. Another might give a detailed technical answer. Both could be correct. Traditional software testing expects exact output. AI systems often require evaluating quality rather than exact matches. And then there is context itself. In many cases, retrieved documents only contain partial information. The system must combine multiple pieces of evidence to produce a complete response. This means we are not simply evaluating an answer. We are evaluating an entire chain of reasoning that spans retrieval, ranking, and generation. And this is why modern RAG evaluation is divided into multiple layers. We don't just ask, is the final answer correct or not? Instead, we ask questions like, was the right context retrieved? Was the retrieved context relevant? Did the answer remain faithful to the retrieved information? Did the model hallucinate? Did the response actually satisfy the user's intent? And this shift is incredibly important because once we stop treating evaluation as a single score, we can begin identifying exactly where the system needs improvement. So before we can build evaluation pipelines, we first need to understand what aspects of a RAG system should actually be measured. So what exactly should we measure in a RAG system? Because one of the most common mistakes developers make is evaluating only the final answer. They ask a question, read the response, and identify whether it seems good. But the approach hides where failures are actually occurring. Remember, a RAG system is not a single model. It is a pipeline of interconnected components, and each component contributes to the final result. That means evaluation must happen at multiple levels. The first level is retrieval quality. Before the language model can generate anything useful, the retrieval system must first bring back relevant information. So, we need to evaluate questions like, did the system retrieve documents that are relevant to the query? Did it retrieve enough information to answer the question? Did it miss critical documents? Or did it retrieve too much irrelevant context? Because if retrieval fails, the generation stage is already at a major loss. The second level is the generation quality. Now that the model has context, how well does it use it? Did the model correctly address the question? Did it remain faithful to the retrieved documents? Did it introduce information that was never present in the context? Meaning, did it hallucinate? At this stage, we are evaluating the behavior of the language model itself. And finally, we have end-to-end system quality. This is a user perspective, because users don't care whether retrieval worked or re-ranking succeeded. They simply care about whether they received a useful answer or not. So here we ask broader questions. Did the response satisfy the user's intent? Was it complete? Was it coherent? Or was it actionable? And could a real user successfully complete the task using this answer? And this identification is extremely important, because a system can perform well in one area while performing poorly in another. For example, retrieval might be excellent, but the model may hallucinate, or the generated answer may be correct, but the retrieval process may be unnecessarily inefficient. Without separating these layers, we cannot identify where improvements are required. And this is why production evaluation frameworks don't produce a single score. They produce a collection of measurements that helps us understand the health of the entire system. And once we know what needs to be measured, the next step is understanding the actual metrics used by AI engineers to measure it. Now that we know the different layers of evaluation, let's look at the actual metrics used to measure them. Because in production systems, we don't rely on opinions, we rely on metrics. Metrics allows us to compare system versions, detect regressions, and make choices based on data rather than intuition. So we'll start with retrieval metrics. One of the most common metrics is precision at k, often written as precision@k. This measures how many of the retrieved documents are actually relevant. For example, if we retrieve 10 documents and only 6 are relevant, our precision at 10 is 60%. High precision means the retrieval system is returning useful context rather than noise. Another important matrix is recall at k. Recall measures whether the system successfully retrieved all the important documents that were needed to answer the question. A system can have excellent precision and still fail because it missed a critical document. And this is why production systems often balance both precision and recall. Then we have mean reciprocal rank, or MRR. This metric focuses on ranking quality. It evaluates how fast the first relevant document appears in the result, because finding the correct document is important, but finding it early is even better. A relevant document at rank 1 is significantly more useful than the same document appearing at rank 20. Now, let's move to generation metrics. One of the most important metrics in RAG system is faithfulness. Faithfulness asks a very simple question. Is the answer supported by the retrieved context or not? If the answers contain claims that cannot be tracked back to the provided documents, the system may be hallucinating. Closely related to this answer is relevancy. Did the generated response actually answer the user's question? A response can be factually correct and still fail because it addresses the wrong problem. Another useful metric is context utilization. Did the model actually use the retrieved information or not? Or did it ignore the context and rely on its own pre-trained knowledge or not? This becomes especially important when dealing with proprietary enterprise data. And finally, we come to hallucination identification, perhaps the most discussed challenge in the modern AI systems. At its core, hallucination identification is simply trying to determine whether the generated answer contains unsupported information. In production environment, this is often one of the most critical metrics being monitored, because a fluent hallucination can be more dangerous than an obvious error. And together, these metrics allows us to evaluate retrieval quality, generation quality, and overall system reliability. But measuring these metrics manually quickly becomes impossible as the system grows. And this is exactly why specialized evaluation frameworks were created. In the next section, we will explore tools like Ragas, dpval, and LangSmith and see how they automate evaluation for modern RAG systems. So at this point, we understand what needs to be measured and which metrics are commonly used. But if you're building a real RAG system, a new problem quickly appears, that is scale. Evaluating a handful of examples manually is manageable. Evaluating hundreds or thousands of test cases every time you update your system is not. This is where evaluation framework becomes essential. They automate the process of measuring retrieval quality, answer quality, faithfulness, hallucination rates, and overall system performances. We'll start with one of the most popular framework in the RAG ecosystem, which is Ragas. Ragas was specially designed for evaluating retrieval-augmented generation systems. Instead of focusing only on the final answer, it evaluates the relationship between the query, the retrieved context, and the generated response. This allows it to measure metrics such as faithfulness, answer relevancy, context precision, and context recall. One of the reasons Ragas becomes so powerful is that it allows developer to evaluate system even when perfect ground truth answers are not available. Next, we have dpval. dpval takes a broader approach to LLM evaluation. It provides a testing framework that feels very similar to traditional software testing. You can create evaluation suites, define expected behaviors, and automatically test your AI system whenever changes are introduced. Think of it as bringing unit testing concept into the world of language models. This becomes incredibly valuable when AI systems start growing in complexity. Then we have LangSmith. Unlike Ragas and dpval, LangSmith is not only an evaluation platform. It is also an observability and debugging platform. LangSmith allows us to trace every step of a workflow. We can inspect retrieval results, we can inspect prompts, we can inspect intermediate agent choices, and we can also evaluate output directly from the same interface. This makes it particularly useful for agentic RAG systems where multiple components interact with each other. Each of these tools solves a different part of the evaluation problem. Ragas helps measure quality, dpval helps automate evaluation, and LangSmith helps monitor and debug complex workflows. And in many production environments, these tools are often used together rather than separately. But understanding the tools is only half the story. The real challenge is building an evaluation pipeline that can continuously assess system performance over time. So in the next section, we will build a complete evaluation workflow and see how production teams systematically test and improve their RAG systems. Okay, so let's put everything together and think of a practical evaluation pipeline. Because in production systems, evaluation is not something that happens once before deployment. It is going to be an ongoing process. So every time the retrieval strategy changes, and every time a new embedding model is introduced, every time prompts are updated, and every time the knowledge base grows, the system must be evaluated again. And this is why mature AI teams treat evaluation as a continuous workflow rather than a one-time activity. At a high level, a production evaluation pipeline looks something like this. It contains evaluation dataset, it contains retrieval system, generation system, scoring layer, evaluation report. Everything here starts with the evaluation dataset. This dataset contains carefully designed test queries that represent real user behavior. Not ideal scenarios, not toy examples, but actual questions users are likely to ask. For each query, we may also store reference answer, relevant documents, expected behaviors, or evaluation criteria. The goal here is to basically create a benchmark that reflects the real-world environment in which the system operates. Once the dataset is ready, we run every query through the retrieval layer. The system retrieves documents exactly it would do in production. Then, the generation layer produces answers using the retrieved context. And at this point, we now have all the information required for evaluation: the query, the retrieved documents, and the generated response. Next comes the scoring layer. And this is where frameworks like RAGAs, DPVal, or custom evaluation models calculate metrics such as faithfulness, answer relevancy, context precision, and context recall. Each query receives a collection of score rather than a simple pass or fail result. And this is extremely important because individual score helps us identify specific weaknesses. For example, low context recall may indicate retrieval problems. Low faithfulness may indicate hallucinations. Low answer relevancy may indicate prompt or reasoning issues. The final stage is reporting. Instead of analyzing individual queries, teams typically monitor aggregate statistics: average faithfulness, average relevancy, average retrieval precision, hallucination rate, and performance trends over time. This allows engineers to compare different system versions objectively. If a new retriever improves recall but reduces faithfulness, the trade-off becomes immediately visible. And this is the real power of evaluation pipeline. They transform your AI development from guessing into engineering. So instead of asking, does this version feel better, we can ask which metrics improved, which metrics declined, and why. And once we reach this level of measurement, we unlock something even more important: the ability to monitor systems continuously after deployment. Because evaluation tells us how a system performs during testing, but monitoring tells us how it behaves in the real world. Now, we need to make an important identification that most beginners miss. Evaluation and monitoring are not the same thing. They are closely related, but they serve very different purposes in production AI systems. Evaluation happens before or during deployment. Monitoring happens after the system is live. Evaluation is controlled, monitoring is real world. In evaluation, we use curated datasets. We run predefined test cases. We know what we are measuring. But once a system is deployed, everything changes. Users start asking unpredictable questions, query distribution shifts, new topics appear, old patterns disappear, and the system behavior begins to drift over time. And this is where monitoring becomes critical. Because even if a RAG system performs well during evaluation, it can slowly degrade in production without anyone noticing. This is known as model drift or system drift. And in RAG systems, drift can happen at multiple levels. The embedding model might become less effective as the domain evolves. The knowledge base might become outdated, retrieval quality might degrade due to new type of queries, or latency might increase due to system load. Unlike evaluation, monitoring focuses on real-time system health. We also track user-level signals. Did the user reformulate their question? Did they abandon the conversation? And did they request clarification multiple times? These signals often reveal more about system quality than any offline test. Tools like LangSmith and LangFuse make this process much easier by providing full traceability of each request. We can see exactly what the retriever returned, what context was passed to the model, and how the final answer was generated. This level of visibility is extremely important in production environment because when something goes wrong, we don't want to guess, we want to trace it. And once we combine evaluation and monitoring, we get a complete picture of the system behavior. Evaluation is going to tell us how good the system should be, while monitoring tells us how good the system actually is. And the gap between these two is where most real-world AI problems exist. Now that we understand how systems are measured and monitored, let's wrap up this video and connect everything into a final summary. So in this video, we explored one of the most overlooked but critical parts of building production RAG systems, which is evaluation. We started with a simple realization that RAG systems don't fail loudly, they fail silently. They produce answers that look correct, sound confident, and feel complete even when they are wrong. And without proper evaluation, those failures are almost impossible to identify. We then broke down why evaluating RAG systems is fundamentally harder than traditional software, because we are not dealing with a single deterministic output. We are dealing with a multi-stage pipeline that includes retrieval, ranking, and generation, each introducing its own potential failure points. From there, we define what actually needs to be measured: retrieval quality, regeneration quality, and end-to-end system performance. And we introduce key metrics like precision, recall, MRR, faithfulness, answer relevancy, context utilization, and hallucination identification. We then looked at how modern frameworks like Ragas, DeepEval, and LangSmith help automate these evaluations at scale. Instead of manually inspecting output, we can now build structured evaluation pipelines that continuously test the system performance. We then extended this idea into a full evaluation workflow, where datasets, retrieval systems, generation models, and scoring layers came together to produce measurable insights about the system behavior. But most importantly, we made a critical identification. Evaluation is not monitoring. Evaluation tells us how the system should behave under controlled conditions, while monitoring tells us how the system actually behaves in the real world. And the gap between the two is where real production issues emerge. Drift, degradation, unexpected user behavior, and hidden failures all live in that gap. So, if there is one key takeaway from this video, it is this: if you cannot measure your RAG system, you cannot improve it. And if you cannot monitor it, you cannot trust it in production. In the next video, we will continue building on this foundation and move deeper into advanced production techniques that make RAG systems more robust, scalable, and enterprise ready. In the last few videos, we focused on building better RAG systems. We started by designing a production-ready agentic RAG architecture. Then we improved retrieval quality using re-ranking. And finally, we learned how to evaluate these systems using metrics, benchmarks, and evaluation frameworks. But there is still a major problem. Even if your system is well designed, even if your evaluation scores look good, and even if it works perfectly during testing, what happens when a user reports that the system is giving incorrect answers? How do you find the actual cause? Was it the retriever? Was it the re-ranker? Was it the prompt? Or was it the language model? Or was it something else entirely? And this is where many AI teams hit a wall. Because unlike traditional software systems, AI systems rarely tell you where they failed. A web application crashes and gives you an error log. A database query fails and gives you an exception. But an AI system can produce a perfectly fluent, high-confident answer while being completely wrong. And the worst part is that the failure often leaves no obvious clues behind. This is why observability has become one of the most important topics in modern AI engineering. Because before you can fix a problem, you first need visibility into what's actually happening inside the system. And that's exactly what this video is about. We are going to learn how production teams trace, debug, and monitor RAG systems. We'll understand what observability really means, why debugging AI system is fundamentally different from debugging traditional software, and how tools like LangSmith helps us inspect every step of a RAG pipeline. And by the end of this video, you will know how to trace a request from a moment the user calls a question or user asks a question all the way to the final answer generated by the model. Because in production AI systems, one principle matters above everything else. If you cannot see inside the system, you cannot trust it. So let's start by understanding why AI systems fail silently and why that makes observability so important. So imagine that you've deployed a RAG application for your organization. Users are asking questions. Everything seems to be working. Then one day, a user sends a message. The AI gave me the wrong answer. At first, that sounds like a simple bug report. But now comes the difficult part. How do you investigate it? Let's imagine the user asked what are the eligibility requirements for self-employed loan applicants, and the system responded with incorrect information. Where did the failure occur? Maybe the retriever failed to find the right document, or maybe the correct document was retrieved but the re-ranker pushed it down the list, or maybe the chunking strategy separated critical information across multiple chunks, maybe the prompt wasn't designed properly, or maybe the language model simply hallucinated despite receiving the correct context. At this point, we all know is the final answer was wrong. We have no visibility into the journey that produced that answer. And that is the fundamental challenge of AI system. Failures are often hidden inside multiple layers of decision making. The answer is simply the final symptom. The actual case or the actual cause could exist anywhere in the pipeline. This is very different from traditional software. When a traditional application fails, we often receive an exception, an error code, or a stack trace. But AI systems frequently fail without crashing. They continue operating normally. They produce outputs, they sound confident, and yet they are wrong. And these are what we call silent failures. And silent failures are among the most dangerous problems in production AI systems because they are difficult to detect and even harder to diagnose. And this is why observability exists. Observability gives us the ability to look inside the pipeline and understand exactly what happened during each request. Instead of seeing only the final answer, we can inspect every step that led to that answer. The retrieved documents, the ranking decisions, the prompts, the model responses, the latency, the token usage, everything. And once we gain that visibility, debugging stops being guesswork. It becomes a systematic engineering process because the goal is no longer to ask why is the answer wrong. The goal now becomes which step in the pipeline caused the answer to become wrong. And that shift in thinking is what separates AI experimentation from production AI engineering. Now that we understand why observability matters, let's answer a more fundamental question. What exactly is observability? Because the term is often used interchangeably with monitoring, even though they are not the same thing. Monitoring tells us what is happening. Observability tells us or helps us understand why it is happening. Think about a traditional web application. A monitoring dashboard might tell us the response time has increased from 200 milliseconds to 1 second. That's useful information, but it doesn't explain the root cause. Observability allows us to investigate deeper and understand what's inside the system led to that behavior. The same principle applies to the AI system. Monitoring might tell us that users are reporting incorrect answers, or that latency has increased, or that token consumption has spiked. But observability helps us trace the entire workflow and understand exactly where those issues originated. And this distinction becomes extremely important in RAG systems because a RAG application is not a single model. It is a collection of interconnected components. A user submits a query is converted into embeddings, the retriever searches the knowledge base, a re-ranker may reorder the result, the selected context is inserted into a prompt, the language model generates a response, and finally the answer is returned to the user. Every one of these steps can influence the final output, which means every one of these steps need visibility. In production environment, we typically want to observe the original user query, the retrieved documents, the similarity scores assigned by the retriever, the re-ranking scores, the final context sent to the model, the prompt itself, the generated response, the latency of each step, and the token consumption, and sometimes even the cost associated with each request. When all of this information is available, something powerful happens. Every user request now becomes a trace, a complete record of how the system processed that request from beginning to end. Instead of seeing only the final answer, we can now inspect the entire decision-making process. And that is the core idea behind observability. Not simply collecting logs, not simply monitoring metrics, but creating enough visibility to reconstruct and understand any behavior inside the system. Because once every request becomes traceable, debugging becomes dramatically easier. And that leads us directly to the next challenge. why debugging RAG system is significantly harder than debugging traditional software systems. Okay, so you might be wondering, if observability gives us the visibility into the system, why is debugging RAG application still considered difficult? The answer lies in the nature of the AI system themselves. Traditional software systems are usually deterministic. Given the same input, they produce the same output. If something breaks, there is often a direct chain of cause and effect that can be traced through logs, exceptions, or stack traces. But RAG systems are different. They are composed of multiple probabilistic components working together, and each component can fail in its own unique way. Let's look at a typical production pipeline. A user submits a query is embedded, the retriever searches for relevant documents, a re-ranker may reorder those documents, the selected context is inserted into a prompt, the language model generates a response, and the final answer is returned to the user. Now imagine the answer is wrong. So at first glance, it might seem like the language model made a mistake, but in reality, the root cause could exist much earlier in the pipeline. For example, the retriever may have written completely irrelevant documents. In that case, the model never had access to the correct information. Or perhaps the retriever actually found the correct document, but the re-ranker pushed it down to a lower position. The answer existed, but it never reached the model. Another possibility is chunking. Maybe the required information was split across multiple chunks during ingestion. The retriever found only one part of the answer, resulting in incomplete context. And then we have prompt-related failures. The correct context may have been retrieved and ranked properly, but the prompt failed to instruct the model to use that information effectively. And finally, we have hallucinations. The system retrieved the right context, the prompt was correct, yet the model still generated unsupported information. Notice what makes this difficult? The same system, a wrong answer can be caused by completely different failures. And without visibility into the intermediate steps, all of these scenarios look identical from the outside. And this is why debugging AI system is fundamentally different from debugging traditional applications. We cannot simply inspect the final output. We need to inspect the entire chain of choices that produce the output. In other words, we don't debug answers, we debug pipelines. And once we adopt that mindset, the next question becomes obvious. If we want to debug the pipeline, what exactly should we be tracing and recording at each stage? Now let's talk about what we should actually trace. Because one of the most common mistakes teams make is collecting either too little information or far too much information. The goal of observability is not to record everything. The goal is to record the information that helps us reconstruct and explain system behavior. So, what should a production RAG system capture? Let's start at the very beginning. The first thing we should always record is the user query. This sounds obvious, but it is absolutely critical. Without the original query, it becomes impossible to reproduce the request later. And reproducibility is the foundation of debugging. Next comes the retrieval layer. For every query, we should record the retrieved documents, basically the metadata, and the similarity score assigned by the retriever. This allows us to answer a very important question. Did the system retrieve the right information or not? If the answer is no, we've already found the root cause. If the answer is yes, we continue investigating. The next layer is re-ranking. If your system uses a re-ranker, you should record the candidate documents, the relevant scores, and the final ranked order. This helps us identify whether important documents were correctly pushed down the list or whether irrelevant documents were promoted. After retrieval and re-ranking comes context construction. And this is the exact information that will be passed to the language model. In many production failures, the issue isn't the retrieval itself. It's how the retrieved documents were assembled into the final context. And that's why we should always record the final context that reaches the model. Then comes one of the most important artifacts of the entire system, the prompt. Remember, the prompt is the set of instructions that governs how the model uses the retrieved information, right? So a poorly designed prompt can cause failures even when retrieval is perfect, which is why prompt visibility is essential. Next, we record the model's response, not just the final answer shown to the user, but the complete generated output. This allows us to compare the response against the context and identify whether hallucinations occurred or not. And finally, we capture operational metrics, things like latency, token usage, model execution time, and request cost, because Production AI systems are not evaluated solely on quality. They're also evaluated on efficiency. When we collect all of this information together, something important happens. Each user request now becomes a complete trace. A trace is essentially a timeline of everything the system did from start to finish. The query, the retrieve decisions, the ranking decisions, the prompt, the generation, the matrix, everything. And once we have traces, we gain the ability to replay, inspect, and understand any request that enters the system. And this is the foundation of modern AI observability platforms. And in the next section, we'll look at one of the most widely used tools for this purpose in the LangChain ecosystem, which is LangSmith. Now, let's move from theory to the actual tool that makes all of this practical in real systems, which is LangSmith. So LangSmith is one of the most widely used observability platform in the LangChain ecosystem, and it is designed specifically for tracing LLM and RAG application. At its core, LangSmith solves one simple but critical problem. How do you see everything that happened inside your AI pipeline without manually instrumenting every step? Because in traditional systems, debugging usually requires explicit logging at every stage. But in LLM applications, this becomes messy very quickly. You're dealing with prompts, embeddings, retrieval, re-rankings, and model outputs all in one flow. LangSmith simplifies this by automatically capturing traces of your entire pipeline. So instead of manually building a logging system from scratch, you get structured visibility into every execution step. Each request becomes a trace, and each trace contains a full breakdown of the pipeline, from the user query to retrieval results to intermediate processing steps to the final model output, and even performance metrics like latency and token usage. What makes LangSmith powerful is not just logging, it is structured observability. You don't just see the raw text logs, you see a hierarchical view of your entire RAG pipeline, which makes it much easier to identify where things went wrong. For example, you can immediately inspect whether the retriever returned 11 documents, or whether the correct document was retrieved but lost during re-ranking, or whether the prompt failed to use the context properly, or whether the model hallucinated despite having correct information. And this is exactly the kind of visibility we need for production AI systems, because without it, debugging becomes guesswork. Now, let's move into the practical part. We'll set up LangChain and integrate it with a simple RAG pipeline so we can start tracing real requests end to end.
Now, at first, I'm going to install LangSmith in my virtual environment. This is the same project folder that I've been using in my previous videos. So let's install this. Okay, the LangSmith library is installed. Now let's go to the LangSmith website. Okay, so you can just log in here using your credentials. So once I've logged in, I'll see this window here. Here I have few projects that I had done earlier. Now from this window, I'll go to Tracing Quick Start and basically create an API key. So let's hit on Generate API key. I'm going to copy this API key and then paste it on my env file here. So for this, I'm going to define the key as LangChain API underscore key. Let's paste this. I'll paste my API key here. Now after this, what else do I need? Okay, let's just copy everything from this line and then we will use it accordingly. So let me paste in everything here. So what I need is, let's remove this export. I need this LangChain tracing. Let's keep this endpoint. I've already pasted my API key, so I don't need this. So the project name is just given by the system itself. Now I don't need my OpenAI API key because I'm not going to use OpenAI on my platform. So this is my basic setup for LangChain tracing. Okay, now we'll just create a new file. Let's call this tracing.py, tracing-rag.py. We'll implement a very simple RAG here. So from LangChain underscore Groq import chat Groq. I'll try to keep it simple just to explain the traceability part here. So LangChain underscore core dot prompts import chat prompt template. Okay, let me define my LLM, which is going to come from chat Groq. Chat Groq, the model name is going to be, as we already used, Llama 3.3, 70 billion, versatile. After this, let me define my prompt. So my prompt is going to be defined from chat prompt template, and let me put from underscore template. Write down my prompt here. My prompt is use the following context to answer the question. Okay. Now put in the context. Provide the context as context, and similarly let's provide question as question. Okay, so once this is done, let me define a chain using prompt LLM. Well, if you don't know how the chain works, you need to go to my previous videos where I have almost a 7-hour long videos dedicated to LangChain or how to use them. So I think if you go to that video and then complete that part, you'll be much more clear on the use of chains and then why we create chains and stuff like that. So we'll just invoke this chain for now. Invoke. We need to pass in the two parameters or the two placeholders that we've created here. The first placeholder is the context. So I'm going to type in context myself. This actually will be created from combination of different chunks, but I'm trying to keep it simple here. So trace LLM applications end to end, and let me pass in my question. So my question is going to be, what is LangChain used for? Okay, it should have been LangSmith, but anyway, I'll just change this to LangSmith. Okay, now finally we can just print out the response. Now this looks to you like a very simple LangChain code or basically something like a chat model here, right? But we've already done something far more important in this to include traces for this particular chain here. So if you run this, I'll just show you how this tracing part works. So let's run this tracing.py. We should get an answer here. Okay. Okay, I think we missed something here. We should also have loaded from .env import load.env to actually load the credential into this file. Okay, now let me just clear this and then run this again. Okay, so this should have been a chat prompt template. I think I messed this again. The import is actually wrong. Let's include chat prompt template here, and then from here let's do chat prompt template and then clear this and run this again. Okay, so if you see, we got an answer from the model. Well, we did get an answer from the model, but if we go back and check our browser, then we should see the complete trace of how the model executed too. Okay, so if you see at this tracing section a few seconds ago, a new project was created and then it basically ran, and the error rate here was 0%. So now let's go to tracing and see
what actually happened here. So if I open this, then we can see the input as well as we can see the output here. The latency was 0.38 seconds. The start time is also given. The total tokens that was used was 86. But since if we go back to our code, we see that we have our entire model divided into two parts. The first is the prompt, and then the second part is the LLM. So let's open this and see what actually happened here. Okay, so you see that we had a runnable sequence, and inside that runnable sequence we used the chat Groq model. So the question was this one: what is LangSmith used for? And then the context that we passed was this: LangSmith helps trace LLM application end-to-end, which we had passed from our model. Now you can see much more details of your attributes for this particular response here. If you go inside this specific chat Groq model, you will see what actually the chat Groq got, or basically what was the prompt here. So the prompt was this, the output provided by the model was this, and then you can see the remaining metadata that the prompt actually gave. So let's also see the input, the output, as well as the attributes. Well, these are all the same thing that we saw earlier in the feedback. So even though we did not add any logging code, LangSmith actually automatically captured our input prompt, the model call, the output response, as well as the execution time. Now, after running the code, you saw that in LangSmith, you saw the full request trace. You also saw the prompt input, what was the input to the model. You also saw the model output as well as the latency. Here we have the latency as well as the token usage here. And now this is where things become very powerful. Now, because we can actually see how the system behaves internally. It is not a guess, it is not an assumption, but this is observation here. So now that we can trace the LLM call, let's extend observability into the most important part of any RAG system, which is the retrieval layer. Because here in production real systems, most failures do not happen at the model level. They happen before the model even sees the context. So if we want to continue debugging power, or if we want true debugging power, we must actually trace retrieval. So instead of providing this context directly, what we are going to do is we are going to simulate a retrieval process here. So for that, what I'm going to do is let's define a simple retriever. Now we have a query for this, or basically we'll get the user provided query, and then since this is a simulation, so I'll just paste in 3 statements here. So LangSmith is used for tracing LLM applications, and one more, LangChain is a framework for building LLM pipelines, and one more, RAG systems combine retrieval and generation. Okay, so we'll assume that this is a retrieval simulation. And finally, what we do from this function is we return the docs, or the retrieved docs, as per our assumption. Now, what we can do is we can define this function called retrieve. Basically passing the query, and from here we can get the results by calling this simple retrieval function, where we pass in the query again and basically return results. Okay, results. Now what I'm going to do is I'm going to add one more import here. So from LangChain import traceable, from LangSmith import traceable, and what I am going to do here is I'm going to add a traceable decorator. Traceable decorator, and then provide a name to this. So the name can be a, let's say it is a retrievers underscore step. Now we'll make a few changes to this. So I will just pass in the query. Let's forget this chain for now. So I'll just pass in the query. Let's say the query is what is LangSmith. And based on this, let's forget this for now. Let's say retrieve docs equals to retrieve query. We're not going for the final answer. We're just checking it for the retrieve docs part here. Let's say retrieve docs. Okay, so once we print this, and then we can run this easily in our system. So the simulated retrieval docs should be printed here. Okay, now this is done, right? Now we go back to our LangSmith. Now, if you see in LangSmith, you have this new trace called the retriever step. And if you open retriever step, then you can see the actual query and then all of the retrieved documents and also the retrieval time here, as well as the attributes basically related to that retrieval. So again, this is a traceable step for retriever here. So LangSmith not only sees the LLM, but it also sees the full retrieval step, which is the input query, the retrieved documents, as well as the execution timing. You can also actually do the same for your re-ranking step. Remember, if you put a function for re-ranking, then you just need to add a traceable here, just like we did in the retriever step, and then you can again see the complete trace of your re-ranking module. And once you combine all of these, your basically model call, your retrieval, as well as re-ranking into a complete model. So now for every request, you will now get a full trace tree. So step 1 is going to be for retrieval, where you are going to see input query as well as the retrieved documents. The step 2 is going to be for re-ranking, where you can see the reordered document. Step 3 is going to be for the prompt construction, where you can see the complete final context provided to the model. Then in step 4, you can see the LLM call, which is the input, which contains the input response or the input prompt, as well as the output response. Now, in this context, your debugging becomes trivial, because if you see some failure in retrieval, you're going to fix the retriever. If you see that your re-ranking is wrong, you fix your scoring logic, as well as if you see that your answer is wrong, you basically check your prompt or LLM behavior. So there will be no guessing, no blind debugging, just a structured visibility. So the key takeaway from this is that observability turns your RAG system from a black box into a step-by-step explainable pipeline. Now that we have full traces of retrieval, re-ranking, and generation, let's do what really matters in production systems. Let's debug real failures. Because observability is not useful until it helps you answer one question: what exactly went wrong? So we'll now walk through some common production failures and how observability exposes them instantly. Consider the first scenario, where the user query was what is the eligibility criteria for a home loan. So maybe the system output was completely incorrect or incomplete answer. So without observability, you would assume that the model is wrong or the prompt is bad. But with LangSmith trace, you find out that the retrieved documents are completely unrelated and document talks about credit card instead of home loans. So now from this, you can identify the root cause that the retrieval system failed and not the LLM. And to fix that, you would maybe work on improving the embeddings or improving chunking or increasing top key results or using hybrid search. Similarly, consider another scenario where the user query was LangSmith usage in production. So maybe the retrieval output was correct or the correct document was present, but after re-ranking, correct document moved to rank 5. So now the top 3 that was fetched or re-ranked were irrelevant. Now, without observability, you would assume that the retrieval is fine, but with trace, you clearly see that the correct document exists, but the re-ranker pushed it down. So the root cause was re-ranking logic was flawed. So you would maybe improve cross-encoder model to fix this, or use stronger re-ranker or tune scoring weights. Now, let's go to the third scenario, where the problem is in the answer, where it is missing the key details. Now, the trace could show that correct documents were retrieved, correct re-ranking was done, but the final context was too long. So, LLM, due to its context length or the limitation in context length, could only see the partial context. Now, we understand that the root cause was due to context window overflow or truncation. Now, to fix that, we would maybe use smart chunk selection, context compression, or summarization before prompt. Similarly, let's look at our fourth scenario. Maybe the system has correct retrieval, correct re-ranking, or correct context, but the answer was in the wrong format, or it completely ignored the context. Now, if you check the trace out, then you saw that the prompt did not enforce grounding. So, which meant the root cause was due to poor prompt design. Now, to fix this, you would maybe work on stricter system prompts, or maybe say answer only from context type of enforcement, or maybe work on some structured output formats. Now, consider fifth scenario, where everything looked correct, but the model added some extra information which was not present in the context. It basically meant hallucinations. Now, the trace showed that the retrieval was correct, re-ranking was correct, prompt was correct, but the response included unsupported claims, which means you can easily identify that the model hallucination was under uncertainty. Now, to fix that, you would maybe apply stronger grounding prompts, or lower temperature, or maybe add faithfulness check, or maybe use evaluation layer. Now, the key insight here is that once you have observability, every failure stops being mysterious and becomes explainable. So, what changes happen in engineering mindset due to observability? So, before observability, maybe you would assume that something is wrong, but after observability, you would definitely say that maybe retrieval step failed at step 1, or re-ranking degraded signal, or prompt caused mismatch. And this shift is what separates beginners from production AI engineers. Now that we can trace and debug every step of our RAG pipeline, the next question becomes even more important. How do we design RAG systems that are built for observability from the start? Because retrofitting debugging is expensive, but building for observability is what production systems actually do. Now let's move from debugging existing systems to something more important. How do we design RAG systems that are observability ready from day one? Because in real production environment, observability is not added later. It is built into the architecture from the beginning. So the key idea here is simple. If a system cannot be traced, it is not production ready. So instead of thinking observability as an add-on, we design every component to emit structured information. So we'll talk about a few principles here. So the first principle that we're going to talk about is everything must be a step. So in a production RAG system, every operation should be treated as a traceable step. That includes query input, embedding generation, retrieval, re-ranking, context building, prompt creation, and LLM call. Each of these steps should be independent and observable. Second principle, structured output over raw logs. So instead of dumping raw logs, we store structured data. It can be query ID, retrieve docs ID, similarity scores, re-rank scores, prompt versions, model versions, and such and many more. So this will make debugging systematic instead of manual searching. So principle number 3, trace ID for every request. So every user query must generate a unique trace ID. This will allow full replay of execution, cross-step linking, and production debugging. Without trace IDs, observability actually breaks down. And in principle 4, version everything. So production RAG systems are constantly changing. So we must always track embedding model version, chunking strategy version, re-ranker version, prompt version, LLM version. Because when something breaks, we need to know what actually changed. In principle 5, store intermediate states. Most systems only store input and output, but production debugging requires intermediate retrieval results, re-ranked outputs, and final context sent to LLM. This is what allows the root cause analysis. In Principle 6, failures must be explainable. So every failure should map to a stage. Which stage? Retrieval, ranking, prompt, or generation. If you cannot classify failure, then observability is actually incomplete. So you need to have this key architecture shift. In the old mindset, we just had query, model, and answer. But in production mindset, you need to have query, embedding, retrieval, which should be traceable, re-ranking should also be traceable, context builder should also be traceable, prompt builder should also be traceable, LLM should also be traceable, and answer plus full trace log. Now, what this enables is once you design systems this way, debugging now becomes instant, evaluation becomes automatic, system improvements become measurable, and production issues become traceable. So observability is not something you add to the RAG system, it is something you build into them. So now that we understand how to design observability for a system, the next step is scaling this mindset into production environment. Because once system grows, we don't just debug them. We need to continuously monitor and optimize them in real time. Now let's talk about what happens when your system goes into production. Because observability is not something you set up once and forget. It becomes something you use every single day. In real world RAG systems, things don't stay stable. Data changes, user behavior changes, and model performance slowly changes over time. Even if everything looks fine on the surface, the system can still quietly degrade. This is why production monitoring is so important. In a live RAG system, we continuously track a few key things. First is the retrieval health. We look at how relevant the retrieved documents are on average. We also monitor whether the system is consistently missing important information or not. Next is re-ranking stability. We check if the re-ranker is consistently placing the correct documents at top, and we watch for any sudden changes in the ranking behavior over time. Then we look at generation signals. We try to detect things like hallucinations, overly long and overly short answers, and whether the model is actually using the retrieved context properly or not. But the most important concept here is something called drift. Drift means your system slowly changes behavior over time, even if nothing breaks. There are different types of drift. Embedding drift, where your retrieval quality starts degrading as your data evolves. Data drift, where new documents change when what the system retrieves. And query drift, where users start asking different kind of questions than before. And the dangerous part of this is everything still looks like it is working, but the quality slowly drops. And if you're not monitoring it, you won't notice until users complain. So in production, we don't just evaluate once. We run a continuous loop. Users query comes in, system processes it, we generate a full trace, we evaluate it, and we update our monitoring dashboards. This creates a feedback loop, a loop that tells us how the system is behaving over time, and more importantly, when it starts to degrade. At this point, your mindset completely changes. You are no longer just building a RAG system. You are running an AI system in production, and one that must be observed, measured, and improved continuously. And this is the key idea to take away. A production RAG system is not defined by how well it performs on a single question. It is defined by how consistently it performs across thousands of real users' queries over time. So once you understand that, everything in RAG engineering starts to make sense. So that's the core idea behind observability in RAG systems. We started with a simple problem: AI systems fail silently. And we ended up building a complete way to see inside them, step by step. From retrieval to re-ranking to prompts to generation, everything becomes traceable, everything becomes measurable. And once you have that visibility, debugging stops becoming guesswork, it now becomes engineering. So if you are building RAG systems, AI agents, or production LLM applications, this is not optional anymore. Because without observability, you're basically flying blind.
In the previous videos, we have built a production-style agentic RAG system. We improved retrieval quality using re-ranking. We learned how to evaluate RAG systems properly, and we added observability so we can trace and debug every step of the pipeline. At this point, many developers think that they're ready for production, and technically they are. But then something interesting happens. The system gets users. A few users become a few dozen become a few hundred, and before long, people start asking questions all day long. Suddenly, a completely new problem appears. Not accuracy, not retrieval quality, not hallucinations. Cost, latency, and scalability. Because the reality is that building a RAG system is actually the easy part. Running it at scale is the hard part. A single query might seem inexpensive, but behind the scenes, that query could involve embeddings, vector search, re-ranking, prompt construction, and a large language model generating thousands of tokens. Now, multiply that by hundreds, thousands, or even millions of requests. What looked cheap during development can quickly become expensive now in production. And it's not just money. Users expect fast responses. They don't want to wait 10 or 15 seconds for an answer. If your system is slow, users stop using it. If your system is expensive, your business model breaks. And if your system cannot scale, it doesn't matter how accurate it is. And this is exactly why production AI systems spend so much time on optimization. Not because they want to, but they have to. In this video, we are going to explore how real-world teams make RAG systems faster, cheaper, and more scalable. We'll learn where most RAG systems waste money, we'll implement different types of caching, we'll reduce token consumption, we'll optimize retrieval, we'll discuss model routing strategies, and we'll look at how production teams monitor cost and performance as traffic grows. By the end of this video, you'll understand one of the most important lessons in AI engineering. The goal is not just to build a system that works. The goal is to build a system that continues to work efficiently when thousands of users start using it. So, let's begin by identifying where RAG systems actually spend their time and money and why many production deployments become far more expensive than developers initially expect. Before we can optimize a RAG system, we first need to understand where the cost is actually coming from. Because one of the biggest mistakes developers make is optimizing the wrong part of the pipeline. They spend days trying to make vector search slightly faster, while completely ignoring the component that is responsible for most of the cost. So, let's break down what happens when a user sends a query to a production system. A user asks a question. The system generates an embedding for that query. The vector database performs a similarity search. Relevant documents are retrieved. A re-ranker may evaluate and reorder those documents. The final context is constructed, and then the language model generates an answer. At first glance, each of these steps seems relatively small, but together they form the total cost of every request. Now let's analyze them one by one. Generating embeddings has a cost. Vector search has a cost. Re-ranking has a cost. Storage has a cost. Monitoring has a cost. Evaluation has a cost. But in most production systems, one component dominates everything else, the language model, and often by a very large margin. Every token you send to the model costs money. Every token the model generates costs money, and those costs accumulate incredibly fast at scale. Let's imagine a simple example. Suppose your system retrieves 10 chunks. Each chunk contains 500 tokens. That's already 500 tokens or into 10, which means 5,000 tokens of context. Then you add your system prompt, then your user query, then the model generates a response, and suddenly a single request might involve thousands of tokens. And if thousands of users are making requests every day, token consumption becomes one of the biggest operational expenses in the entire system. But token usage isn't the only problem. Many RAG systems repeatedly perform the exact same work. The same questions get asked again and again. The same documents get retrieved. The same answers get generated. And yet, the system recomputes everything from scratch every single time. Think about that for a moment. If 100 users ask the same question, do we really need to run 100 expensive LLM calls? Probably not. And that's where optimization begins. Not by making the model smarter, but by eliminating unnecessary work. Because in production system, efficiency is often more valuable than raw capability. And one of the most powerful ways to eliminate unnecessary work is through caching, which is exactly where we're heading next. Because a properly designed caching strategy can reduce both cost and latency dramatically, often with surprisingly little effort. Now that we know where the cost comes from, let's talk about one of the most powerful optimization techniques in all of software engineering, which is caching. In fact, if you ask experienced engineers how they make systems faster, one of the most common answers you'll hear is, do not do the work twice. And that's exactly what caching allows us to do. Instead of repeatedly recomputing results every time a request arrives, we store previous results and reuse them whenever possible. This simple idea has been used for decades in databases, web applications, operating systems, and distributed systems. And it turns out that it works incredibly well for RAG systems too. We'll start with the simplest form of caching, response caching. Imagine a user asks, "What is LangSmith?" The system performs retrieval. The system builds a prompt. The language model generates an answer and we send that answer back to the user. Now suppose another user asks the exact same question 10 seconds later. Should we perform retrieval again? Should we call the language model again? Should we spend more tokens generating the same answer? In many cases, the answer is no. We can simply return the previously generated response. The result is almost instantaneous, and more importantly, we avoided another expensive LLM call. But response caching is only the beginning, because exact question matching has limitations. Users rarely ask questions in exactly the same way. One user might ask, "What is LangSmith?" Another user might ask, "Can you explain LangSmith?" And a third user might ask, "What is LangSmith used for?" These questions are different, but semantically they are asking almost the same thing. This leads us to a much more powerful concept, which is semantic caching. Instead of checking whether two questions are identical, we check whether they are similar in meaning or not. If two questions are sufficiently similar, we may be able to reuse the same answer, and this dramatically reduces both cost and latency in real-world problems. There are other types of caching as well. For example, embedding caching. If you have already generated an embedding for a piece of text, we can store it and reuse later. No need to call the embedding model again. We can also cache retrieval results. If the same query repeatedly retrieves the same documents, we can store those results and avoid unnecessary vector searches. Notice what's happening here. We're not making the model faster. We are simply avoiding work that we have already done. And that's often where the biggest performance gains come from. Because the fastest request is not a faster request. The fastest request is the one that never had to be executed in the first place. Now that we understand the different types of caching, let's implement the simplest and most common one first, response caching. And you'll see how easy it is to start saving both time and money. Now let's move from theory to implementation. We'll start with the simplest caching strategy, which is response caching. The idea is straightforward. If we have already answered a question before, we store the answer. Then, if the same question appears again, we return the stored answer instead of running the entire RAG pipeline. Think about what we are avoiding. No retrieval, no re-ranking, no prompt construction, and most importantly, no LLM call, which means lower latency and lower cost. So, let's build it. So, we start with imports. So, from LangChain _Groq, we'll use the model first, or we'll try to import the library for the model, chat_Groq. Now, let me do one more for prompt. Import chat prompt template. Okay, so now let me define my LLM, which is going to be chat_Groq. The model name is Llama 3.3 70 billion versatile model. Okay, so I'm going to build a very simple prompt here. We can use the same in our RAG application too, but I'm going to show you the caching strategy using a very simple example. So prompt equals to chat prompt template. Okay, it should have been chat prompt template. So chat prompt template dot from template. Let me pass in a multi-line string here. And my prompt is going to be answer the following question. And I'll pass in my question in the form of question placeholder. And that is it. Okay, so this is going to be my prompt. Let me just reorganize this. Now let me define a chain. So my chain will have a prompt as well as a single LLM call. Okay, so we'll use something for our response cache here. So let me do a very simple data storage for our response cache. So this will be used as our response cache. Now let me define a function to get an answer where I will pass in my question in the form of a string. So instead of directly calling the LLM or directly invoking this chain, what I'm going to do is I'm going to check if my question is present in response cache or not. Now, if it is present in the response cache, then I'm going to say cache it. And I'm going to return the response cache, which is corresponding to my provided question. If not, then I will have to go for a new LLM call because this question has never been asked previously. So response equals to chain dot invoke. So I will need to pass a question here. So I'll pass a question and ask. Let me just do question for now. Okay. Now the answer is actually present in response.content. So I'll just try to separate the answer part. And what I'm going to do is I'm going to add this to our response cache. I'll add in the question as a key and answer as its current value. And then I will pass the or return the answer that we retrieved from LLM. Now we can test this. So my first question is going to be, what is LangChain? Okay. Now I'm going to get my answer from my getAnswer function where I can pass in the question. Then I can print the answer easily. Again, I will ask the same question and then get the answer in answer 1. Basically the same question. And then let me print my answer 1 here. Okay, so also let's add a separator so that we won't get confused which is answer part and which is answer 1 part. Okay, so this is going to be my separator. Now let me call this or run this code. So Python response caching.py. If we don't have any errors, then this code should run properly. So what we have done here is introduced a response cache variable where we have stored every new question and corresponding answer into that particular data storage above. And then before we answer any question or before we send it to LLM call, we first check whether that particular question is present in the response cache variable or not. If it is present, then the previously generated answer is shown to the user. If not, then we come to the LLM call part, and then we basically send our query to the LLM and generate an answer for the question. And again, we save that answer in our response cache itself so that it can be used for the next API calls. Okay, so I think I forgot to load my API key since I already have it in my .env file. So for that, I need to do for .env import load.env, and I need to basically call this function. Now let me clear this and then run this again. Okay, so if you see here, if you see from the very beginning, the first request goes through the LLM. So basically our LLM generates a response for our first question. So the response is up to this part. And then when we ask for the second question, then the second question never touches the model. Instead, the answer is returned immediately, checking on the cache. So since the question and answer was found in cache, so here we have a cached scenario, and the same answer is repeated again and then provided to the user. So what happened here? On the first request, our user query was sent to LLM. We generated a response from there, and then that response went to cache. Now on second request, user query was first checked in cache, and if found, that was generated, or the response was taken from the cache itself without calling the LLM. So you can see how much work we eliminated here, even in this simple example. The language model was never called in our second query. And since LLM calls are usually the most expensive part of the pipeline, even a small cache hit rate can produce significant savings. For example, if 30% of your queries are repeated, you can potentially eliminate 30% of your LLM cost. If 50% are repeated, you may cut your cost in half. Of course, there is a limitation here. This only works when the question is exactly the same, right? If one user asks what is LangChain and another asks can you explain LangChain, then the cache we've implemented won't recognize them as identical, even though they are asking essentially the same thing. And that brings us to one of the most powerful optimization techniques used in modern AI systems, which is semantic caching. Instead of matching the exact text, we'll match meaning, and that is where things start getting really interesting. Now let's take caching one step further, because exact match caching is useful, but it has a major limitation. Like I said, users don't always ask the same question in the same words, because human language is flexible, right? The same idea can be expressed in many different ways. For example, what is LangChain? Explain LangChain to me. Why do developers use LangChain? Tell me about LangChain. All of these questions are different from a text perspective, but from a meaning perspective, they are very similar. And this is where semantic caching comes in. Instead of storing the questions itself as the cache key, we store its meaning. And the way we represent meaning in AI system is through embeddings. An embedding converts text into numerical representation. Questions with similar meanings produce embeddings that are close together in vector space. So the workflow now changes. Whenever a new query arrives, first we create an embedding for that query. Then we compare it against previously stored query embeddings. If we find a similar enough query, we reuse the cached answer. Otherwise, we continue with the normal RAG pipeline. Now, this creates a much better and much smarter cache, because now the system understands similarity, not just identical text. Then let's implement a simple semantic cache. We will use the LangChain ecosystem with HuggingFace embeddings. The idea here is store the previous question, its embeddings, and its generated answer. Then compare new questions against the stored embeddings. So let's start with the code part. Here from LangChain underscore HuggingFace, we will import HuggingFace embeddings. Then from sklearn, I do have sklearn here. So sklearn dot matrix dot pairwise, I'm going to import cosine similarity, which is useful for comparing our embedding vectors. So let me define my embedding model here. So embeddings equals to, this is going to come from HuggingFace embeddings, and the model name is, please be careful with this name. So this is sentence transformers all mini LM L6 V2. Okay, so I might have to install this sentence transformers library here. So let me do that quickly. So pip install sentence transformers. This might have already been installed, or we might have to install it again. Let's see. Okay, so the requirement is almost already satisfied. So I think we've already installed this in our virtual environment. Now let me define a semantic cache storage, and I'm going to define this as a simple list. Okay, now to store our cache, what I'm going to do is I'm going to define a function called store cache, where I'll have a question and I'll have an answer. Now, first of all, what I'm going to do is I'm going to convert my question into embeddings. So question embedding equals to embeddings dot embed query, and then I'm going to embed my question. Now I'm going to add this into my semantic cache. Okay, so semantic cache dot append, and inside this I'm going to add few parameters. I'll first add in the question, which is going to be my question. Second, I'll be adding embedding, which will be my question embedding. And third, I'm going to add in my answer. Then this will contain the value for answer. Okay, so now that our embedding has been stored, so let me define another function where we search our cache. So let me minimize this a bit, and then I'll write down a new function to search our cache. So def search cache. Here I'll provide a question, and then since the language is going to be different for even the semantically similar question, so I'm going to define the threshold here. So let's keep the threshold at around 85%, which is 0.85. Now what I'm going to do is I am going to search in semantic cache. If the semantic cache is not present, then I'm going to return nothing. But if the semantic cache is present, I'm going to do query embedding and then convert my query into embedding using the embedding model. Now I'm going to search through my semantic cache for a similar question. So to find the similar question, again, we are going to use a score, which is the cosine similarity score. And this cosine similarity score is going to compare the following. It is going to compare the query embedding. It is going to compare item embedding. And I'm just going to break down the result. So let me just do 0 and then 0. Just extract the cosine similarity. If we run across any errors, then we'll just rectify this. Now, since this particular value provides us a score or a threshold score, I'm going to compare it against my defined threshold. So if this is greater than or equal to the threshold of 85%, then I'll do semantic cache hit, and I'm going to return its corresponding answer. Or if I don't find anything, then I'm simply going to return none here. Okay, so this is almost done. Now we are going to combine this into our RAG system. Now let us define what we had done previously. So we will need all of these models. So let's go and use it in semantic caching. We'll need everything. We'll also need our LLM definition, as well as the prompt and the chain too. So let's use everything from LLM to the chain part. So I'll just paste it here. So we have the model name, our prompt, as well as the chain here. Now, what I'm going to do is I'm going to do a semantic RAG part here. So let's define a function for semantic RAG. I'll pass in the question. So this will basically look for the cached answer based on the search cache function on the question, basically this particular function. And if we don't have semantic cache, it will return none, and then go on to embed that particular question here. And then if it finds anything on semantic cache that is remotely similar based on the threshold to the provided question, then it will return its answer, or else it is going to return none. So if we get something from that function which is cached answer, then we simply return the cached answer. Or if we get none, then we need to go and then run our LLM pipeline, which means we don't have that cushion of caching provided to us right now. So for this, what I'm going to do is I'm going to run my chain. So I'm going to invoke this chain based on a question that I'll provide. So the question is the question variable, and similarly I can separate out the answer from here, which is response.content. Okay, and then once this is done, we can store this cache using the store cache function, where I need to pass in the question as well as the answer, and basically return question from here. Now what I need to do is I need to call this function. So let's go to response caching, and then basically call what is LangChain. What is LangChain? Let me get my answer from response. Sorry, this should be return answer, not return question. So this should be semantic RAG call, not semantic cache, semantic RAG call with the question. And I'm going to print the answer here. So let me print answer. Let me add a separator with a double line break, and then change in my question and ask explain LangChain to me. Then I will pass in, then I will again pass in the question or the new question to semantic RAG function question, and then I will print in the answer here. So basically what should happen here is we don't know what the similarity between these two questions is going to be, but I hope it is going to be greater than 85%, but we'll check it out. And then if this particular question invokes the model and then our semantic caching is complete, then this particular question should be solved from that semantic caching part, which means the model should not be called. Okay, anyways, we'll test it out using our terminal. So let's go to new terminal. I already have a previously open terminal. I'm just going to use it here. Let me clear this. Let me save my code and then run Python semantic matching.py. Have I printed the last answer? Well, I have, so I can just run this. Okay, let me stop this for now because I think I made a mistake with the question. What was there? So the question was explain LangChain to me, and what is LangChain? So let me clear this and then run this again. We'll definitely get a response. We just want to see if our semantic caching approach works or not. Because we have two different LLM calls, actually 3 different calls to an API. One is going to be for LLM and 2 other calls for our embedding model. So this will be somewhat slower than the previous request that we've done in our response caching. So at first we run the LLM. Let me go here again. So if you see here, at first we run an LLM pipeline. It basically calls the model and generates an answer. And then we've added a separator here. Then once we pass in the second question, then we see a semantic cache hit instead of the LLM call, which means the 2 questions that we have provided, even though they're not same in terms of wording, are actually similar semantically. So this particular answer is not being generated from the LLM call, but it is being generated from the cache response that we had previously saved from this particular first question here. So I can clearly say that this does work too, or the semantic caching does work too. And this is a much more realistic caching strategy for AI applications, because real users do not repeat exact sentences, they actually repeat intentions. And semantic caching allows our system to basically understand that intentions. But caching is only one part of optimization. So another huge cost factor in RAG systems is something we've already seen many times: the amount of context we send to the language model. Because sometimes the problem isn't the model itself. The problem is that we're sending too much information to it, and that is where token optimization and context compression come in. Now let's talk about one of the biggest hidden costs in RAG systems, which is tokens. Every time we send information to a language model, we are paying for that information, right? And many RAG systems waste a huge number of tokens without even realizing it. So the common mistake is simple. Developers retrieve documents and then send everything they retrieve directly to the LLM. And at first, this kind of seems reasonable, because more context should mean better answers, right? But that is not always true. More context can actually make the system worse. We'll consider a simple example here. Basically, when a user asks what is the refund policy, the retriever returns 10 documents. Let's suppose each document contains around 500 tokens. That means we are sending roughly 5,000 tokens of context to the model. But maybe only 1 or 2 of those documents actually contain the answer, and the rest is just noise. So what happens? We pay for unnecessary tokens and our response becomes slower, and the model has to process a lot of irrelevant information. And this is where content optimization becomes important. Now, the goal is not to send more information. The goal is actually to send the right information. And there are several ways we can achieve this. The first method is improving retrieval. A better retriever is going to give us better documents. Instead of retrieving 10 weak results, we retrieve 3 highly relevant results. The second method is better re-ranking. The retriever might find many possible documents. The re-ranker will help identify which one actually matters to us. And the third is context compression. Now, this is a very interesting idea. Instead of sending the entire document to the model, we first compress the retrieved information. We remove unnecessary parts and we keep only the sections that directly help us answer the question. And the result, the model now receives much less information and the information quality significantly increases. Think of it like studying. So if you want to learn a new topic, you don't want someone to throw an entire textbook at you, right? You just want the important chapters, the important pages, the important paragraphs, and the same idea applies to LLMs. And this optimization has a huge impact. Less context means lower cost, lower latency, less chance of distraction, and often better answers. Because large language models are powerful, but they still need focused information here. Now, we can implement this idea So basically we'll use a LangChain technique called a contextual compression retriever, and the workflow will change from query, retriever, all of the documents to LLM to basically query, retriever, compression layer, relevant context, and then to LLM. So the compression layer that you find here will act like a filter. It will ask whether the piece of information actually help answer the question or not. If yes, if we keep it, if no, we basically remove it. And this is one of the most important optimization techniques in production RAG systems, because the cheapest token is the token you never send. So let's try to implement it next. Okay, let's implement this context compression part. So let's start from importing our libraries. Please install the LangChain Chroma. If you don't have it, you can just install it using pip install LangChain_Chroma. I already have it installed, so I can just import this directly. Then we will again need an embedding model. So I'm going to use HuggingFace Embeddings for that. For our RAG documents or documents that needs to be included in our RAG, so I'm going to use this document library. Then for prompts, let me use chat prompt template. Then I will have a runnable lambda here. Then to load my environment key, I will have load.env, and I'll call this load.env function to load my environment key. Okay, so now let's define our LLM. So like we did earlier in our response caching, we are going to use the same model here. So I'm just going to copy this and then put it as my LLM. Now I'm going to bring in a few documents. So let me define a document list. So this is going to be a list, and here I'm going to add documents to this. So let's add the first document. You can just paste, you can just pause the video and then copy this, or you can refer to our repository link that is provided down below, and then copy your documents from there. So I'm just going to copy paste this and not type it completely. So the second document, so the first document is about LangSmith, the second document is about LangChain, the third document is going to be about VectorDB, the fourth document is going to be about Python. And I will have 4 different documents that I'm going to ingest into my RAG system. Okay, once this is done, I will need to define my embedding model, but like I did earlier, let's go to semantic caching and then use the same model from sentence transformers for embeddings in our context compression tool. Okay, so the model has been defined here. Now, since we installed LangChain Chroma, and Chroma is going to be used as our vector store, so let's define our vector store. So this will be done using Chroma. So chroma.from_documents, and for documents, I'm going to pass my documents variable that I've just created earlier. For my embedding, I'm going to use my embedding model, or just use this embeddings. Then let me save my vector store so that it can be reused. So this will be named a compression demo. Okay, Once the vector store is initialized, now I'm going to define a retriever using this vector store dot as underscore a retriever, and my search keyword arguments will say that I am always going to look for the top 4 results for my search. It should have been equal to here. Okay, so now my retriever is also done. Now what we're going to do is we are going to define our context compression layer. So for that, we are going to write a detailed prompt template providing precise filtering instructions to the model. So for that, let me define extraction prompt. Now this extraction prompt will use the chat prompt template. Chat prompt template dot from underscore template. And again, I'm not going to copy the entire thing here. I'm just going to, I'm not going to type the entire thing here. I'm just going to copy paste my prompt. So let me just paste this to view, word wrap, so that it becomes easier for you. Okay, so my prompt reads, given the target user query and a document context block, extract only the verbatim facts that directly correlate to answering the query. If the document block does not contain any information related to the user query, reply explicitly with no relevant context. And I passed in the page content, the user query, and then I am expecting an extracted content block here. So what this is basically going to do is, even if I retrieve the top 4 documents for my query, now this is going to go through each and every document and then label it whether it is relevant to answering the question or not. And such no relevant context documents are going to be filtered out later on whenever I'm going to pass it to this final LLM. Basically what we're going to do is we are doing this context compression part by filtering out this no relevant context documents. Okay. So now let me define an extraction chain. So this extraction chain is going to contain extraction prompt. And along with this, I'm going to include an LLM here. Now, what we need to do is we basically need to evaluate all the retrieved chunks and then dynamically filter blocks using an LLM here, right? So I am going to define a pipeline for this. So my contextual compressor pipeline is going to consist of input, which will be in the form of dictionary. And then this will return a list of documents, list of document. And inside this, now basically what this function will do is, let me write a comment for this. So this is going to evaluate retrieved chunk and dynamically filter blocks using an LLM. So here my query is going to come from inputs. I'll put it in query and then extract it from there. Then I will take my retrieve docs from inputs and then documents. And finally, I'll put a list or create a list for my compressed docs. At current, this particular list is empty. Now, for every retrieved document, I'm basically going to run an extraction chain. So this particular extraction chain is going to be invoked. Now, what do I need to pass here? I need to pass in 2 different things. One is the page content. So the page content is going to be doc.page_content. And the second parameter is going to be query. For this, I'll have a query variable. Now, whatever response I get, I just want the content of it, not the metadata. So let me do extracted text equals to response dot content dot. Let me just strip it out. Response. Okay. Now, I am going to filter out the no relevant context documents. So for that, let me write a conditional statement. So if extracted text is not empty and no relevant context, let me just verify this and then use the exact same key because I'm comparing the key here. Okay, so no relevant context not in extracted text, which means the extracted context is relevant to the question. I'm going to add this to our compressed docs. Append document. The page content is going to be extracted text, and in metadata we'll have doc.metadata. Okay, now from this, once my compressed docs is retrieved, I can pass in compressed docs. Okay, so what I can do is I can convert this contextual compression pipeline into a runnable Lambda here. So for that, let me do compression layer equals to runnable Lambda. Now I'm trying to bring this into my LangChain ecosystem. So contextual compressor pipeline. Now once this is done, let me now write my RAG prompt. So my RAG prompt is again going to come from chat prompt template. Let me just copy this because I don't want to type everything in detail. Okay, I think the function name is mistaken here. Let me just copy this function name, contextual compressor pipeline, and then paste it here, contextual compressor pipeline. Okay, so the RAG prompt says answer the question using only the retrieve context. I pass in the context and then the question here. Now, what I can do is I can define a function def ask RAG where I'll pass in the question as string, and then what I'm going to do at first is I'm going to use my retriever and then extract the relevant documents that the retriever found, basically the top 4 documents that the retriever found to be suitable to our question. Once the raw docs is achieved or extracted, then I'm going to run this through our compression pipeline. So compressed docs equals to compression layer. I think I've defined it as compression layers. So compression layer dot invoke invoke. I can pass in my question or query as question and documents as raw docs. Now let me define my context string. So I'm going to combine everything that I have extracted in the compressed docs. Basically it is a list. So I'm going to convert all it into a single string here. So for doc in compress docs, I need doc.page_content. So now for my response, I can simply call my RAG prompt, RAG_prompt, and then an LLM. Basically invoke this chain where I need to pass in two different things. One is the context, which is going to be my context str, and then the other is going to be my question, which is my question itself. Now, whatever it returns, I'm going to return it in this function. So at first, I'm going to return my answer, which is going to be response content. Next, I'm going to return documents used, where I'll pass in length of the compressed docs, basically the filtered document length. And then for the context, I'll pass in the context str. Okay, so everything is now set up. Now I can simply call askRag function and then pass in a query. So what is LangSmith used for? So if you see in our document list, we have one single document that talks about LangSmith, right? But since we are retrieving the top 4 result from our vector store, it is going to extract the top 4 most relevant documents for our query here. But we also have invoked a compression layer after we've extracted our retriever. So this compression layer should actually drill down into each of the document and then remove those which are not relevant to the question. And based on it, it should basically call my RAG pipeline and then generate an answer along with the actual document or the actual number of documents that has actually been used to answer this particular query using our RAG pipeline, not the original number of retrieved documents here. Okay, so for that, and to verify that, what I can do is I can simply print the result. So this particular result is going to come inside our answer. So let me do answer, and if I want to check how many documents were relevant, so number of relevant documents, if I can just print this out, I would basically do result and documents used. Okay, I think this should solve our problem. So now let's run this and then see whether our context compression layer works or not. So let's go to my terminal and then run Python context compression.py. The code was quite long, so we might have made some mistake here, but we'll check. Obviously, we do have a mistake. So the first problem is with this context str. I think this should be invoked inside a curly bracket. Okay. Now let's clear this and then run this again. Since a multi-layer LLM call is invoked along with conversion of document into embeddings, storing it into vector store and whatnot. So it will take some time to run in the previous run or in the first run, but from the second run, since the vector store will already have been created, so it will just run the semantic search and then it will move to the compression LLM API call and then basically provide us the result. Okay, so we have got our error. Ignore this LangSmith error. I think there is some problem with the project key that is embedded in the LangSmith, and then ignore this LangSmith error here too. But I think we got the correct answer. LangSmith is used for debugging, monitoring, and evaluating LM applications. And then we can see that the number of relevant documents was actually 1. So what the model did was it actually retrieved the top 4 documents from this particular connection. So this might have been retrieved, another LangChain might have been retrieved since the word lang is present. Another vector databases might have been retrieved, and maybe another Python document might have been retrieved too. So all of these 4 documents could have been retrieved by the model, but our context compression layer actually drilled it down back to one single relevant context, as we can see here, and that context was used to generate our final answer. So this is how we implement context compression using the LLM itself. And then this is how the context compression works, and then prevent the usage of access token. If we compose our context compression along with our semantic caching, then we would have implemented or we'll be successful in implementing some form of optimization approach in our RAG, and then we can similarly use this for agentic RAG too. So let's summarize what we did in this video, or everything we learned in this video. So building a RAG system is only the first step, right? A system that works in a demo environment does not automatically become a production-ready system. So once user or real users start interacting with it, new challenges appear there. The first is cost, another is latency and scalability. So a powerful model alone itself is not enough. What we need to do is we need to make smart engineering choices around how the system uses resource. So we started by understanding where RAG systems spend most of their resources. So we found out that every query can involve embedding generation, retrieval, re-ranking, context processing, and finally the language model. And in most cases, the biggest cost came from the language model itself. So every token we sent, every token we generated basically added up. Then we looked at caching. So instead of repeating expensive operations again and again, we learned how to reuse previous work. We started with simple response caching, where identical questions could instantly return stored answers. Then we moved to semantic caching, where the system understood that the different question could have a different meaning. So this basically allowed us to reuse answers when the wordings were changed. And then after caching, we focused on reducing unnecessary context. Now, because more context, we understood that more context does not always mean better answers, and sending too much information increases cost, latency, and sometimes even reduces the answer quality. So we introduced the context compression layer, where the system filtered, retrieved documents, and sent only the most useful information to the model. So the key lesson from all of these techniques is actually very simple. Production AI is not about using the biggest model everywhere. It is actually about using resources intelligently. So a good AI engineer does not just ask, how can I make my model smarter? They also ask, how can I make my system faster, cheaper, and more efficient? Okay, so in this video, we'll end this video because this has already been too long. So in the next video, we'll continue optimizing our RAG architecture and look at another powerful production technique, which is model routing, where instead of sending every query into an expensive large model, we intelligently choose which models should handle each request. So simple questions could use smaller, faster models, while complex questions could use more powerful models. And this can dramatically improve both cost and its efficiency. So if you found this video helpful, make sure to like the video and subscribe to the channel. And if you're building RAG systems, AI agents, or production LLM applications, stay tuned because we are going deeper into real-world AI engineering. And now I will see you in the next one.